Pleasure to introduce to you our first speaker for tonight. So he has a bachelor's degree in civil engineering from Mindanao State University. He is a registered professional civil engineer and a registered materials engineer, and also a member of Structural Engineers Association of Davao. He has worked in different engineering and construction firms, both local and international companies, for the past 22 years with vast exposure in design and construction. He has engaged in various types of design activities ranging from small to medium structures, such as buildings, gymnasiums, short-span bridges, FM tower, and covered court. He uses finite element analysis on all complex temporary works, those having risk category A and category B. Those structural analysis including existing bridge, assessment, and immediate solutions. He has worked on infrastructures under US aid, Louis Berger Gym, Program Trading Center, boat landings, short bridges that includes medium span, 100M pedestrian suspension bridge, manufacturing plants such as fertilizer plant, banana processing plant, and banana chips plant. As a freelance designer and engineer, he has engaged in the design of Agape Partners Academy, a 3-story building, and sewage treatment plant, elevated water tank under JICA program in Davao City. In addition, he has joined Holcim Philippines, now Lafarge Holcim, doing the role of a CapEx and project civil engineer in the design of medium steel structures for publication inside the cement plant. So without further ado, it's my pleasure to introduce to you our first speaker for tonight, Engineer Arthur Omar.
Thank you, Sir Rex Pahinado. Good evening, fellow engineers. Good evening, students. I hope this 2-hour webinar will give you at least a relief after this session. So let me share to you my screen. Can you see it now? Sorry, it started on the fourth. Can you hear me loud and clear?
Yes, sir. We can hear you.
Okay. So my topic is about temporary work shoring tower, to which we really use this one in our recently completed project in R10. And the next part is about analyzing a moving load. So I think this would be very relevant because nowadays, especially the build program, a lot of projects like NACR, the railway projects here in the Philippines, most of the contractors are really preparing or giving their tenders in participating those bids, the mega project. So this is just a part of those projects that we have recently completed. Now, let me show you the next screen. So the topic is bridge erection using design shoring towers. So why we need to use this shoring towers? As I have said in the previous webinars, we have introduced the function or the importance of temporary works as a support or as will pave the way of the permanent works. So this one, the next part is the 420-ton lancing girder. This is a moving load exercise to cross on a 100-meter span, balance cantilever.
Hi, Sir Arthur.
Yes.
Excuse me lang po. Sir, di po na yun makita yung screen niyo po.
Wait. Sorry.
Thank you.
Can you see it now?
Yes, sir. Can see it now. Thank you.
Yeah. So the next part is the 420-ton launching girder. Why I tend to use this topic because it's really appropriate, because nowadays, especially the Philippines, we wanted to connect the north and south using the railway projects by Japanese government. So this is just an exercise to appreciate how a software will work, how the power of a certain software will work on predicting or analyzing the influence lines resulted by moving loads on the balanced cantilever. So we have some few codes like the Japan Transport Engineering Company, because they are the ones giving this project, especially their light railway system. And the next one is the famous ASTO LRFD bridge design code. And lastly, I included the EIC 360-10 for steel design. So those are the codes. We just limit the codes because this is more about exercise and about temporary works. So let me just define to you a simple philosophy, which is almost all of the designers are using nowadays. Simple philosophy is the limit state design. This is about a resistance factor. This LRFD is the same as LSD and LRFD. It refers to a design method used in structural engineering. It's a limit state. It's a condition of a structure beyond which it no longer fulfills the relevant design criteria. What does this mean? So, for example, if you design a simple bridge, simple span bridge, and then you will load it more than what is the accepted moving load in the code, like the heaviest moving load we encountered, the XL93, the ASTO HS20, that's 44. Those are truck loads and some lane loads effect. So those are the accepted loads on this simple limit state design philosophy. But if you further increase that loading beyond the code requirement, beyond the code allows, or beyond the limit of the code, then the bridge, like the predefined ASTO girder 1, 2, 3, 4, 5, they are stress girder PCDG, which are already has defined capacities. So if we make loadings beyond what is really accepted in the code, then those bridges will fail, or those will have local damage to the members of the bridge. So this limit state design is just the limit or the boundary that we designers must not allow that it should be below this limit state. For example, I designed a shoring tower, and the capacity of the shoring tower is based on the codal based design is 100 tons. So if the actual load will exceed more or less 150 tons more, or it becomes 150 tons, then surely by the code and the actual performance, surely it will fail. Although we don't know what is the catastrophe, what is the extent of failure, but surely by the code requirement, it will fail. So our role is not to exceed those limits. So this is the excellence of the limit state design. The condition may refer to a degree of loading or other actions on the structure. Next slide. The limit state design, although it's a philosophy, its main purpose is to ensure safety, serviceability, and economy of the design. So why we need this three aspects? Because engineering is more about safety to the public, economy, and serviceability to the public. It will give comfort to the people. The excellence of limit state design lies in clarifying how these objectives are to be achieved. So paano po natin makukuha yung mga objective na yon? Paano natin masigurado na yung structure natin will not fail, or what is the degree of safety or the margin of safety, or if it will fail a little bit, it will crack or it will deform a little bit, what is the remedial actions, or can we use that building after that certain earthquake or whatever forces that may damage the building, or will just evacuate right away. So there are conditions. Re-examines the process of design. It re-evaluates the margins of safety employed to cover uncertainty and ignorance, because the design, especially we are humans, we are not perfect. Our designs are just assumptions. Even the code requirements are just there to guide us in following those limits, not to exceed those limits in order to have that margin or certainty of safety. So we are not perfect. For example, let me tell you a short story related to the design. The perfect, because we have this called limit state design, we have also another thing, the performance-based design. Some are more about risk design or more about uncertainty. And lastly is the resilience design base. These are a lot of evolution of design philosophies that may tend to correct the weaknesses of every design. Like the first design aspect without this these philosophies are the intuitive design base. Ibig sabihin noon, yung mga tao, nagde-design sila ng mga building or structure through experience lang. Tinitingnan nila, it will stand, hindi ito mag-collapse kasi ganito kalaki yung column. So, yun, ang intuition lang kasi wala pa silang mga base ng code, not yung experiences nila, yung effect ng environment and everything. So, those are the evolution of design philosophies is really complex, but as we can see, there is a harmony also. So, I will tell you a story. The perfect design is the design of our creator. That's perfect. Why? For example, if you design a helicopter is patterned in the, what do you call that? Kung sa Alindanao, sa Bisaya, the dragonfly. And also, if you see an eagle, the design of an eagle, the robustness of the wings of an eagle, it's related to the robustness of design. If the eagle can fly and it will surmount very strong wind pressure. But how about the chicken? The chicken cannot fly like an eagle. So we say it this way. There is already a need. Before the eagle has been created, there is already a need. So there's a need to design that bird, to make it very robust in the wings, the design of the wings, the aerodynamics, the shape, the strength of an eagle. There is already a need. So ibig sabihin po, merong nakatingin na talaga na perfect designer kasi nakikita na yun eh. Kung hindi siya, kung tsamba lang muna, hindi ma-perfect yung design na yun. So it's like buildings. Buildings, since we are humans, we are not perfect, but the experiences and evolution of the code will tell us that this is another improvement from one code to another. So say, now I'm talking about the limit state design, because what I'm showing to you in the next slides is a simple design of the Turing Tower, because I think it doesn't need a robust or extingency of the code, especially it's only temporary. And we know that temporary structures are only there maybe a few weeks or few months or a year, but it will not stay long because the permanent works will come in and then we remove everything, the temporary works. Next slide. Limit state method recognizes as a result of influence of several factors affecting safety and serviceability. So yung imposed load, yung effect ng magbabari siya doon sa mag-affect sa kanya yung serviceability and safety due to the imposed load and due to the strength of materials na ginagamit, yung mga material na yon. So it's very important that we have also a sub-study or sub-field in civil engineering, which is more about the materials. So next. it's expressed in terms of the probability that the structure will not reach at the limit state. It's going to be a simple statistical term because there is a term probability that the structure will not reach at the limit state. Bakit ibig sabihin, bakit probability? Because we are not certain perfectly. Hindi natin masabi na yung structure natin hindi talaga mag-fail or gaano ka ang yung degree ng ano niya, robustness o hanggang kailan siya hanggang mag-attain siya ng ultimate strength, yung rupture, yung plastic state. So it expressed in terms of the probability that structure will not reach at the limit state. So yun lang talaga, i-limit na natin. So yung mga code na papansin natin, meron siyang reduction like steel Fy 0.6 Fy, and even using the finite element, you will reduce the stress, the allowable stress, the demand versus capacity. Usually the demand, yung capacity natin is reduce pa natin para meron pa tayong margin of safety kasi meron tayong sinasabi nga uncertainty kasi hindi tayo perfect. So code-based design calcs must aim in keeping the probability of the limit be attained below a certain value. So hindi natin, pwede rin iba, isasagad talaga nila kasi define masyado yung mga material, but in the sense na may mga sinasabi na may tinatawag tayo na mga matatapang na designer. Hindi sila natatakot. So we have yung iba nga 1.0 na, wala nang safety factor pero nag-go pa rin sila. So yun ang risk ng designer. Kaya nga meron tinatawag na designer's risk assessment. Next, ultimate limit state or limit state of collapse. Yung ultimate, ito ang ibig sabihin, sinagad mo na yung material like, for example, in the concrete, the 0.85 FC prime AB in the beam, yung sa compressive block natin, i-maximize mo yon. Pag nasagad mo na yung ultimate limit state na, so may tendency na siya na magkakaroon na siya ng mga cracks kasi sinagad mo na yung material eh. So ultimate na yung capacity niya, pero hindi pa rin mag-fail, hindi mo rin masabi na mag-fail siya kasi mag-perform pa rin siya, especially steel. While the next one is the serviceability limit state or SLS. Yung normally, pag nag-design tayo using serviceability limit, kailangan din yan, hindi lahat ultimate kasi magiging uneconomical yung design natin. Kasi kung serviceability ka muna, wala ka muna mga factor sa loading mo, for example. So ang titingnan mo lang yung sa service ng structure like before the NCCC Mall in Davao was burned. Yung nasunog kasi yung NCCC Mall in Davao. So pag nakapasok ka ng NCCC Mall, you will walk and then you will feel really the strong vibration of the floor. So ibig sabihin yung mga tao natatakot sila kasi bakit na-vibrate ng malakas. So yun na papasok yung serviceability limit state, yung ibig sabihin, yung serviceability ng building, although hindi siya nag-collapse, parang hindi ka naman masyado komportable kasi nag-vibrate ng malakas yung floor. So, kailangan i-address din yun ng design natin. Kaya nga, tinatawag na meron tayong mga limits kasi dapat hindi rin magiging matakot yung public. Kahit sabihin mo hindi mag-collapse, hindi rin malakas yung vibration dapat. So, next. ULS, the max load capacity of the structure, yung ultimate limit state, is sinagad na nga. So, itackle niya yung mga forces like flexure, bending, shear, torsion, whatever forces na magkakaroon ng stress sa structure, na masagad siya, yun yung ULS. And then, yung mga phenomena na magpipail siya is magkakaroon ng loss of equilibrium, yung number 1. Member or the whole structure, yung part lang ng member, may maputol na bracing, and then magkakaroon na siya ng weakness doon, then the whole structure also, mag-collapse na siya, about to collapse. The next one is the failure of critical section. Yung mga section na, for example, bridge, napakatibay nung bridge mo, pero nag-load ka ng crane sa taas na may outrigger na napakabigat, 600-tonner crane, tapos yung outrigger mo diretso doon sa slab ng bridge mo, then critical failure, yung sa tinamaan mismo ng outrigger, mabutas yun. So, ibig sabihin, may failure siya, critical siya doon kasi diretso siya eh. So, dapat spread mo yung load. So, yun ang tinatag, hindi nag-fail yung bridge, pero nabutas naman yung slab. So the next one is plastic hinge formation. Yung plastic hinge kasi magkakaroon na yung mechanism yan na magkakaroon ng hinge yung structure mo, like for example viaduct, bridge, napakalakas na seismic activity like level 2 earthquake, tatama siya sa pier mo. Normally ang mangyayari is magkakaroon siya ng plastic hinge doon sa malapit sa support. Based on study sa Caltrans, napakarami, 85% yata doon ng failure. Kaya nga yung mga bridge na tinamaan na napakalakas na earthquake, doon magpifail yung sa baba sa support, tapos matumba yung column, tapos mahulog yung mga beam. So ibig sabihin catastrophic yung effect, and then the only culprit is yung plastic hinge formation. So paano ma-resolve yun? Kailangang robust na naman yung design mo, tapos dahil nga sa advanced computer na yung ginagamit natin ngayon, we are modeling finite element software using static, dynamic analysis and everything. So mapipredict na yung mga iyon. At the same time, may mga code requirement na dinadagdag na para hindi mahulog yung beam, lalagyan na siya ng seismic restraining rod para mapigilan lang. Kasi based on study, nahulog yung mga bridge type sa US. So yun ang effect ng plastic hinge formation. Number 4, the buckling due to elastic instability. Kasi yung buckling, kailangan i-consider yan kasi magkakaroon, dalawa kasing force involved yan eh. Axial at saka bending. So kung pag itulak na yung column, napakabigat na dadalhin ng column, tapos mahaba yung column mo, magkakaroon siya magbe-bend siya at the same time, axial, napakalaki. So mag-buckle siya, maputol siya. So meron tayong tinatawag na slender column or short column. So ibig sabihin, slender column, yung Euler Euler formula ng mag-burn. So buckling. So ibig sabihin, titingnan din natin na dapat hindi siya mag-fail through buckling. And then lastly, fatigue failure. Yung fatigue failure is it's a phenomenon na palagi kang tinitira. Merong for example, yung tubig tumutulo yan na isang spot lang at a very long time na hindi siya mag-stop magtulo ng tubig. Pwede niya sirain yung material kasi concentrated siya pabalik-balik, or like the moving loads of railway, train. So the train, pag magpalagi siyang tumatakbo tapos biglang hinto, yun, magkakaroon ng fatigue yung structure, yung railless at saka yung railway mo. Kasi yung fatigue is, although repeated siya at saka cyclic loading siya, para kang sinusuntok ng mahina hanggang sa manghihina ka kasi mahina lang ng suntok pero palagi hindi siya mag-stop. So yun ang fatigue failure, may cyclic siya na. Next. SLS normal use of the structure criteria. Simple lang yung serviceability limit state. Yung limit state of deflection, dapat masatisfy natin. Hindi masyado mag-excessive deflection like beams. Yung slab, meron tayong L/120 or L/240. Yung mga beams sa code requirement natin, kailangang i-maintain siya para hindi magkakaroon ng excessive deflection that may cause discomfort to the public. Next is the limit state of cracking or local damage state. So, yung cracking naman, although hindi naman delikado, hindi pa mag-fail yung structure mo, pero kung cracking na excessive naman, mini-measure yan eh. For example, we have conducted assessment of silo in Davao. Titingnan namin yung crack ng silo kasi may isang silo doon na bumagsak sa Davao, sa Holcim. So, yung titingnan mo sa assessment is yung degree ng crack, gaano kalapad na yung crack. So, pag masyadong na siya, more than the allowable, so delikado na siya kasi lalabas na yung mga reinforcement mo. So it's more about the state of cracking. So it's more about local damage state. And lastly, we have the limit state of vibration. So normally you can find this limit state of vibration in manufacturing plants like machine design, machine structure. Lalakas ng mga vibration, dinidesign namin dun sa machine foundations. So, malakas. At kahit building, pag malakas ang earthquake, tapos matagal siyang maghuhupa yung earthquake, hindi kakayanin ng lalo na pag ang magnitude is more than 7.8. That's what happened in California, or yung tinatawag natin the big one. Yung the big one na mamaya i-explain ng co-speaker natin na si Engineer Valencia yung seismic. But that big one, hindi natin alam kung anong magnitude yan. Some may say mga magnitude 13 daw. So wala nang tatayong building yan. So those are predictions. So limit state of deflection, cracking, and vibration, dapat i-ano mo yun, i-limit mo lahat para yung design mo is functional. Tumayo naman yung building mo pero nag-sway at saka nagba-vibrate, hindi siya magandang walang mag-rent ng building mo. Walang uupa, walang mga tenant kasi matatakot. So yun ang SLS at saka ULS. Next, we can't hindi natin pwedeng walain the robustness of a design. Kasi ibig sabihin yung robustness is the ability of the structure, parang manhid siya sa, insensitive siya sa local failure. Like yung pinakita ko na tower na yan, parang titingnan mo masyado maraming bracing, or like the bird's nest in China, Beijing, napakaraming mga bracing, parang tingnan mo parang art lang siya, pero at the same time structural component siya. So napaka-robust niya, so marami siyang redundant elements. So hindi mo, pag naputol yung isa, hindi pa rin magtutumba. Puputol yung another member, hindi pa rin matumba, hindi pa rin mag-collapse. So yun ang robustness. So this prevents misuse. Halimbawa, yung bridge mo, may mga misuse kasi ng pedestrian bridge na case sa US na nag-collapse yung bridge kasi yung mga tao, ang dami nila, nagsabay sila, parang lumulundag sila, then nag-vibrate, nag-oscillate yung bridge, sabay. Hindi nakayanin yung nung bridge. Nag-collapse siya. So ibig sabihin, hindi yun accident. Sinadya talaga yun. So this prevents misuse. So dapat robust yung design natin. Then some are accidents. Mabangga yung matamaan ng mga backhoe, yung existing structure, impact, and some explosion, accident din yan kasi hindi natin ma-predict yung explosion. Hindi natin alam kung gaano kalakas except yung nasa Middle East ka, gagawa ka ng bunker structure na kaya niyang mag-resist ng explosion na napakalakas, like 2-meter thickness na mga walls, reinforced, so mga ganun. So robustness in design. Fire resistance. So yung hazard ng fire kasi to ensure the integrity and carrying capacity of the structure for a defined period of time. So kaya nga sa code natin, sa National Building Code, they are imposing that this material should be fire rated like at least 2 hours or like that. Kasi pag masunog ka agad yung wall mo ng 10 minutes, wala nang bumbero. Useless na ang bumbero. Hindi na kayang habulin ng bumbero kasi patatakbo pa ang bumbero. So kung may fire rating ka na 2 hours, kaya pang abutin. Kaya nga yung mga bumbero napakabilis dapat. Kasi 2 hours lang mga fire rating normally. So yun ang mga i-consider din natin sa design. Next. Durability is the ability to resist from the environmental condition. Ito yung last na natin na hindi natin i-neglect. So durable, yung common word na durable talaga matibay. Pero ang ibig sabihin ng durability is nakatayo yung structure mo kahit anong environmental load, kaya niya. Normally, environmental load sa ibang bansa mas marami. Meron silang snow, whatever loading, mga cyclone. Or, sa atin to may typhoon, pero wala tayong snow. So paying attention to material specifications, quality control, and workmanship, dito papasok ang QA/QC. So durability, more on material. I-control natin. Kaya nga meron tayong mga exam ng materials engineer 1 and 2. So dapat focus din tayo ng field na yan kasi hindi lang lahat design, hindi lang lahat more on forces, but also the quality of material. So it's more about the routine protection and preventive maintenance. So gagawa ka ng routine protection and preventive maintenance, durable yung mo, like marine structure, kailangan yung paint mo na marine din, so hindi siya magkalawang kaagad. The corrosion will not act right away, so magkakaroon pa rin siya ng longer life. Next. All limit state must be considered in the design. Yung diniscuss natin lahat, mga ULS at saka SLS limit state, yung serviceability at ultimate, and nandoon na yung deflection, yung cracking, vibration, lahat ng mga limit state na yun, robustness at saka yung mga additional parameters like the durability, dapat i-consider natin sa design. So makikita mo yung graph na yan, dito lang tayo sa baba ng straight line kung limit state lang tayo. Hindi natin lampasan yung papunta na tayo sa ultimate. Pero yung ultimate naman, kailangan mo rin i-design yung ultimate kasi yun yung collapse. Magko-collapse yung, dapat naka-design siya ng ultimate kasi dapat hindi siya mag-collapse during a strong earthquake na pwede pa siyang ma-repair yung building mo. So may tanong nga kung na-collapse yung essential facility mo, nag-collapse, tapos yung mga bumbero at saka yung mga rescuer, anong code ang maggagawa na naman na yung mga rescuer yun ang magpo-protect sa kanila. Kasi yung mga rescuer sila magpo-protect after the calamity or the hazard, the strong seismic yung activity. Sino naman yung magpo-protect ng mga structure na yun kung nag-fail din hindi nila nag-fail din yung mga iyon. So meron pang additional na tinatawag na ULS plus, yung tinatawag nila sa ibang design, another philosophy. So next, this is now the proper I will just show to you the simple erection sequence using this shearing tower that we have. A lot of these towers are being used in our project. So as you can see there, there is a plan view of the crane, and then this is somewhere here in Dimasalang. This is just a study because this is part of our tender. Yung ginawa namin design lahat sa tender kasi kailangan titingnan lahat yung tender stage na design, although preliminary design pa rin siya. Pero makikita mo, nakaplan na lahat yung crane erection at saka yung girder na i-erect mo at i-lift mo at saka i-place mo sa shearing tower. So that's an example. The next slide, as you can see, dalawang crane magkasabay, kinukomplete nila yung isang girder kasi naka-segment siya, 3 segment. So yung tower naman ng dalawa na sa gitna, yun ang pinapatungan, yun ang di-design natin. So the third slide, itong nakikita natin, nakompleto na niya yung isang stretch. So nailagay na niya yung isang maiksing segment. So we are good to go. Ngayon, nasa simply supported state pa siya kasi nakapatong pa lang siya. So the load path there is just simply supported. Halimbawa, ang weight ng gitna is 2 kg. Ano ko lang para madali. Yung sa kaliwa is 1 kg. Yung sa kanan is 0.5 kg. So kalahati ng 0.5, kalahati ng 1 kg, ma-distribute sa isang shearing tower. Yung isa naman kalahati, ganyan. Kasi simply supported pa siya. So madaling i-predict. But in the case of pag na-splice na yan siya, nag-continuous na siya, iiba na yung load path niya. Mag-change na ng load path. So magkakaroon na siya ng hindi na natin ma-predict yung sinasabi na hati-hati. So that's the time you have to analyze it as continuous beam. So, kaya mong i-solve yan using any method, of you have a software like STAAD Pro or Midas or whatever software. Kaya mong kasi simple frame lang siya, simple beam lang siya, but continuous. So mahirap din siya imano-mano kasi matagal kung continuous na o magkaroon ka ng matagal na calculation, manual. So here comes a software magagamit mo diyan, so mabilis mo ma-anticipate kung ano yung reaction ngayon sa dalawang shearing tower na yan. Ito yung shearing tower na yan at saka ito yung isa, magkaiba yung reaction niyan kasi mas maiksi ito eh. So pag na-connect na yan lahat, mag-change na yung load path, hindi na ma-apply yung simply supported na distribution na half-half ng loading, ng weight ng girder mo. So next. Here, makikita mo rin sa profile ng bridge, kasi simplified na to eh. More on tender stage kasi ito. Kikita mo yung profile ng bridge, malalaman mo gaano kataas yung pier. At saka meron pang data ng diyan eh, borehole data ng soil, ng geotechnical. So here, another closer look ng dalawa kasing steel girder na box yan eh. Ipapatong mo diyan sa shearing tower na yan. So as you can see there, the shearing tower, and then nakapatong na yung yung dalawang steel box girder mo, yung nakaharap sa taas ito. And then ito yung sa naka-side view siya. Ngayon, ang tanong is paano mo ma-ensure na itong shearing tower is kaya na yung patong na yan? So number one is alam mo na yung weight ng mga girder na yan, total weight, kasi nakukuha yan sa theoretical like using software, Tekla software, or you can using truck scale, titimbang mo yan lahat, makukuha mo yung exact weight. But Hindi lang yun, kasi pag doon ka lang, kukulangin ka kasi meron pang maraming superimposed load na mangyayari after na ilagay yan. Meron pang diaphragms and everything, mga lifting frames, mga railings, maraming mga dagdag na weights dyan. So, diaphragms lang, masyadong mabigat na. Hanggang sa magiging permanent siya. So, temporary state pa tayo ngayon. Kikita mo. And there, you can see, it's a 41.99 meter span ang distance niya sa tower to tower. So, lagay mo lang yung weight ng uniform dead load weight ng girder. Ito yung niya, equivalent na loading diagram. May konting wind load tayo kasi in reality, may wind load talaga na tatama sa tower mo na yan. So, i-account mo rin yan. So, we're just using this as SLS, serviceability limit state. Hindi muna tayo ng ultimate dyan. Yan. So, here's an example of the STAAD Pro input. I-input natin yung mga parameters, like meron na siyang built-in sa code niya, and then the basic wind speed here in Manila, normally the 260 kph, 55 mph meter per second. Yan yung gagamitin natin, and then crush tower structure type. So, input mo lang lahat, and then pag na-input mo na yan, magbibigay yung ASCII calculation na automatic siya, makukuha mo na yung pressure diagram. So, nakukuha mo hanggang sa taas. Kung mapapansin mo to, ito yung dalawang girder na nakapatong. Hindi lang siya hanggang dito yung hangin, matatamaan pa niya yung dalawang girder na nakapatong. So, dapat i-predict mo yun. Hindi lang yung, dito lang yung wind load mo, maniglect mo to, kukulangin ka. So, in actual, meron tong load na tatama na hangin. So yan, i-account mo rin yan. Kaya yung height ng diagram is umabot talaga sa height ng girder na pinatong. So yan yung isang niyan. So software lang kaagad, makikita niyo yung mga pressure based on code ASCII 7. So next, ito yung distribution ng forces. So two-dimensional kasi yan na ganyan, pero in reality, three-dimensional siya. May tatama din going to your screen, yung nahangin. And then, lahat i-account mo yung all direction ng loading, ng wind load. Here, sinimplify na natin. Magkakaroon na siya ng point load doon sa tower. Yung sinabi nga natin kanina, yung nakasplice siya. Tapos, yan, meron kang load definition. I-run mo na naman yung computer. Makukuha na niya ngayon yung internal forces due to that loading sa internal forces ng bawat member ng tower mo. So, ang maganda lang sa software kasi meron na siyang built-in code optimizer, or meron siyang code, kailangan niya mag-take off siya kagad. Pwede niya magsabi na optimize or malaki, ito yung pinaka-economical. Pero hindi siya AI na para siyang designer na ito yung pinaka-economical at saka ganito yung lahat. Ito yung size ng girder, ito yung size ng column, ito yung size ng bracing, but the computer will just tell you individually. Like ito yung pinaka-economical, but magkaiba yung sizes. So ikaw na mag-proportion ng sizes. Yun ang basic. Ang trabaho ng designer ngayon, magpo-proportion na lang. Pag assuming tama yung input mo ng software, ang gawin mo na lang, magpo-proportion ka na lang kasi ibibigay na niya yung pinaka-economical. But still, the design philosophy, kailangan mo rin i-maintain yung sinasabi natin na serviceability limit state. Hindi siya masyadong malakas yung sway para hindi siya magkakaroon ng crack or yung vibration or yung deflection na within the certain limit lang. So that's the concept of using the load definition and using this software. So the analysis result, ang pinaka-importante, makukuha natin yung reaction doon sa tower. So may reaction yung tower, meron kang axial, yung Y forces, yung going down, and then you will also have a corresponding moment sa certain ng tower na yan. So diniin na siya, at the same time may bending din yung na-experience yung tower mo. So combined stress, kayang i-cater sa software yan, i-design na naman niya yung mga combined stress na yun. So bibigyan ka na niya ng section. So, bibigyan ka ng diagram, shear diagram, maximum shear, makukuha mo dyan, and the figure, makita mo, napakalaki. Kilonewton, nasa 940 tons yan 9402. So, yan yung shear diagram. And then, it will also give you the moment diagram. So, makukuha mo yung maximum axial load ng combined loading ng mga girder at saka yung mga components. And then also the maximum moment na may experience ng tower. So in that case, madidesign na ng computer yung tower mo. Next, as you can see there are max nodal displacement. Kaya iti-check mo yung displacement. Kaya nga, kasi ang visibility nga ng structure, hindi lang na porket kaya niya yung structure, hindi mo na pabayaan mo na siya mag-sway o mag-deflect ng malaki. So, by that, ibibigay din ng computer gaano kalaki yung displacement. Kahit mabigat yung nakadiin, pero nagdi-displace pa rin siya ng 8.2 mm. So, yan yun, mapipredict mo. So, allowable, pwede siya, maliit lang siya. We have that some code allowance like L over 240 or the story drip of a building, merong ganun. So, here, as you can see, sa right side, ito yung mga values na yan yung mga utilization ratio ng mga member. So, ang computer, magbibigay sa iyo na ito, halimbawa, 0.174, 17.4% utilized. Ibig sabihin, ang safety factor mo nasa mga 80%, kayang-kaya. Pero the more na mag-close siya into 1, o saka ang computer, magbibigay siya, kung failure siya, magbibigay siya ng red color. Kulayan niya kaagad. So, madali mo ma-determine kung ano yung failed members. Di tulad noon, wala pang computer, napakahirap yung mga trabaho ng mga designer noon. Mga trabaho ni na Harvey Cross, ni na Castellano, ni na yung mga forerunners ng structural engineering, ni na Flo, wala pang masyadong powerful computer, but they managed to develop the basic fundamentals of structural engineering using manual, without calculator, using abacus, using slide rule. Kaya pa rin, tumayo pa rin yung mga building natin. Next, as you can see, ito yung steel take-off. Ang computer, meron din siyang capability to give you a take-off sa material. So, halimbawa, meron kang W8 by 18, bibigyan niya yung haba at saka yung weight in terms of kilonewton. So, ma-predict mo kung anong total weight ng tower mo. As you can see there on the bottom, 54.5 tons. So, yan yung total weight ng tower. So, malaman mo ngayon kung in terms sa cost, ma-estimate mo na gaano kamahal yung tower na yan. I-plus mo lang yung mga component like bolts and gasket plates and everything, like concrete pads na papatungan ng tower and guy wires. Kailangan i-guy mo para meron siyang redundancy in overturning, at saka yung global stability din niya, meron ding support. Hindi lang nakatayo lang siya, meron kang redundancy dapat ng support. Next. There, the top platform, dapat robust siya. Nakikita niyo, ito yung actual na project namin. Itong top platform, robust siya. Dito ipapatong kasi, itong platform na ilagay yan sa taas, tapos itong platform na to, dito papatong yung mga girder mo. And especially this picture, ang girder na papatong dyan is curvilinear. So, magkakaroon siya ng non-linear effect, dynamic non-linear effect kasi curvilinear siya. So, mahirap i-predict. Magkaroon siya ng tilting on the X direction, X axis. Meron din siyang twisting on the Y and some whatever rotational effect. Kasi yung girder is curvilinear. Kung straight lang siya, okay. Like yung kanina, pinakita ko straight yan. Pero this tower, ito yung ginamit namin. Itong platform na to, ginamit pa rin namin yung tower na to sa straight. Pero ang original talaga niya is it is performing to support a curvilinear beam. Next. Here, you can see the seismic design. Meron tayong basic lang na seismic. Actually, this tower should not be designed by using seismic code, but kailangan mong i-perform pa rin yung seismic design kahit maiksi lang to, mga nasa 25 meter high lang siguro. And why I included the seismic design here, because it's very important to use the proper, these mga parameters na yan, makikita natin. And especially the R, the response modification factor of towers like open towers, the moment resisting space frame, may mga 8.5, meron yan sa code natin sa NECP, iba't iba yung mga ng R. But very importantly, yung R talaga, dapat tama yung paglagay mo kasi in this kind of tower, ang naka-default sa STAAD is I think 3. The R is 3. I think something is 3. The value is 3. Pero sa totoo, based on studies, yung history pala, na-underestimate niya yung yung value. Bale, dapat ang totoong R sa mga open frame tower is nasa ano lang 2.45 or 2.5 maximum. So doon pa lang kukulangin ka na. So dapat dapat yung study mo based on yung performance ng structure mo ng steel, ng open frame ng tower is based, importante yung R. Pati yung mga parameter na to importante. Itong period naman, kayang i-compute ng STAAD yan. Bibigay siya ng Rayleigh frequency ka agad. So makukuha mo yung period or pwede mong rule of thumb na kung ano kung building siya, every floor nasa 0.1 second siya. Kung 10 floor yung building mo, nasa 1 second yung period. More or less lang. Hindi nalalayo doon. So these are the parameters here for the static equivalent static force procedure ng UBC 1997, which will be expounded by our next speaker. It's more about seismic. Sinali ko lang dito para ma-appreciate natin na kahit tower yan, kailangan pa rin ng seismic design. Ipakita natin. Next. Ito yung sinabi ko na R na response modification factor na itong 8.5 sa building yan. Pero itong ginamit ko dito sa STAAD input is to 2.5. Kasi yun ang totoong R nito. So, ito yung mga near source factor. Actually, yung NA and NB yan, importante din yan kasi nung wala pa na-invento yung mga code na to, yung lumang code pa, maraming nag-fail. Yung Kobe Japan na earthquake, nag-fail siya kasi kung magkaiba kasi ang effect ng earthquake, pag tumama siya sa building mo, tapos yung strata ng soil mo is malambot dito, iba yung effect kung matigas masyado yung hard soil yung tinatayuan ng building mo, iba naman yung kung soft soil siya. At doon din may function din na yung kalakas ng earthquake na yun, normally in Mexico, may nangyari na yung mid-rise building ang nangatumba, nag-collapse, and then most of the high-rise and the low-rise nag-stand because the oscillation of the ground is the same, yung natural frequency ng structure na mid-rise. So, masyado malaki yung effect, catastrophic, nung nag-fail yung mga mid-rise building. So, yun, gumawa sila ng study. Ngayon, nag-improve yung code natin, ginamitan ng mga near source factor na to. So, itong period na simple fundamental period formula at ito naman yung seismic response coefficient na nasa code, ipa-plug in mo lang. So, next. The period also very important kasi magkakaroon kasi ng top force doon sa taas eh. So, meron siyang condition na ganito, kung less than 0.7 seconds, ito yung ito yung period, kung less than yung period mo ng 0.7 seconds, or therefore FT equals 0, mga ganun. So hindi nalalagyan ng additional force sa taas. So those are codal based sa parameters in lateral seismic design, static lateral procedure. So there you can see the result. Yung tower, nakakaroon na siya ng stress diagram kasi pinarana natin yung computer based on those inputs. At mapapansin mo, magkaiba yung mga stresses niya kasi may effect ng hangin. Kung mapapansin natin dito, it's more about seismic kasi ELF to eh. Nakikita mo yung load dito, ELF, equivalent lateral force response. Oh, yeah, ELF. This is more about static procedure, the effect of that one. The next one, you can see, this is now, I also included a dynamic input kasi pinatry kong makuha yung result kung mag-apply ako ng dynamic. Pero actually, hindi na kailangan ng dynamic to kasi kahit sa code nga, 25 story or less than 50 meters, hindi ka na kailangan muna mag-dynamic unless irregular yung structure mo, yung shape niya. But this time, although it's, I think, 25-meter height tong tower na to, nilagyan ko, pinaano ko pa rin ng dynamic analysis, which is the simple response spectrum analysis, para ma-appreciate natin na magkaiba yung effect, yung nodal displacement, ano yung effect ng forces using those modal participation factor ng effect ng dynamic sa ground motion mo. So, next. Ito yung isang simple na nag-animate siya sa dynamic using the response spectrum analysis. Exaggeration lang yan, pero mapapansin mo, ma-appreciate mo yung effect. Marami kasi yan eh, yung 6 fundamental mode lang ang binibigay ng default ng computer. Magkaiba yung movements niya. So ito, short tower yan. So ang effect niya, ito yung base shear niya. base shear along X, ito base shear along Z. Papapansin natin, itong square root of sum of the square, tawag dito itong SRSS sa computer, naka-built-in yan. Yan yung famous talaga na model combination ng na formula na matagal na ina-accept until such time na meron ng bagong formula na dumating, which is the CQC. So may advantages yung dalawa na yan, pero normally ngayon, pinaka-famous na ang CQC kasi accurate to eh. Hindi siya mag-overestimate, hindi din siya mag-underestimate kasi i-incorporate yung sign ng participation factor ng force at saka displacement. So ibig sabihin, SRSS 113 yung base shear niya, yung lakas nung sa ground, yung base shear, while using the CQC 141. So masyadong malaki ang diferensya. Ibig sabihin, accurate yung CQC. Kung titingnan mo naman dito, 117, malaki pa rin dito. But makikita mo, maiksi yung short tower kasi siya. So kung short tower siya, malaki talaga ang CQC. Mas mag-prevail ang CQC kasi more on closely spaced kasi siya na interval ang CQC. Effective siya sa closely spaced interval like 1.1 seconds, 0.2 seconds, tumama yung seismic. So yun yung effect ng CQC. The complete quadratic na formula sa complete quadratic combination to sa pag-combine ng modal participation. So dito, mapapansin natin, nag-move yung malaki yung effect. So makikita mo, CQC, yung base shear mo, 141. Pero para lang makipakita natin yung effect. So next slide, sinubukan kong ipahaba yung tower. Dinagdagan ko siya ng another 50 meter. So nagiging 75 meter high na tower. Ang result ngayon, ang square root of the sum of the square is RSS 51. Ang CQC 57, lumapit siya. Ibig sabihin, bakit lumapit? Kasi malayo na yung frequency, yung gap ng time, malayo siyang makabalik. Tingnan mo, mahina eh. Kasi mataas siya eh. Yung period niya. So, ibig sabihin, dito pareho sila. So, magagamit mo dito ngayon ang SRSS pag ganito napakataas na mga structure. But still, CQC is more consistent using this one. So, sa STAAD output, makikita mo to, ito yung base shear effect ng dynamic analysis ng using the span spectrum. So, a lot of things like nonlinear dynamic, you are using yung meron din tinatawag ang software ng time history analysis, meron ding input doon. Pero in this case, hindi na siya kasali. Pinakita ko lang yung span spectrum ng tower na yan. And then, para ma-appreciate natin na lumiit yung CQC dahil napakataas nung toll yung yung tower mo. Okay? So next slide, ito yung response spectrum niya. Input niya, naka-1 lang yan lahat. Actually, kung building yan, you need to scale up ang result ng dynamic base shear. Kung halimbawa, ang static base shear na nakikita is 500, ito 51 lang, scale up mo siya ng 10 times 10 or times 9 para magiging 90%. Nasa code yan. Pero in this case, pinakita ko lang na 1 to para ma-appreciate natin na totoo talaga yung sinabi ng code na the more na mas matagal makabalik yung structure, mag-sway yung modal participation niya, first mode, mag-sway siya, then magagamit mo yung SRSS. Pero kung masyadong mababa yung sway niya, magagamit ng CQC. Yan yung mga advantages at saka difference nila. Next, yung abs naman, yan yung malaki masyado. Siya ang pinakamalaki. Makikita mo palagi siyang malaki. Absolute kasi yan eh. Plus lahat. Plus lahat yung pati dito, 144 siya, 151 siya ang pinakamalaki. So hindi siya economical kung gagamitin natin. So dito tayo sa CQC or SRSS. Next, that's the simple graph sa NSCP na ipa-plug in mo yung span spectrum na data, acceleration against time. So i-plug in mo lang din sa STAAD. So magbibigay na siya ng response spectrum. It's a pseudo-static, pseudo acceleration and pseudo velocity. Makukuha mo lahat. Lahat ng pati displacement at a certain time. So very famous tong dynamic analysis na to, pero may limitation to siya. Kasi nasa linear ka rin. Linear state ka lang. So pagdating na ng linear, hindi na applicable yung dynamics tool na to doon na tayo pupunta sa mga nonlinear analysis like using time history or what we call some pushover analysis or any analysis na na ano ngayon na popular. So next, you can see the tower. Itong tower na to, na design na yung mga section, nagsasabi siya, ito yung size ng angle bar, 150 mm by 150 mm by 10 mm. Yan yung size. Naka-optimize na siya sa computer. So, ibig sabihin, pasado siya. Then size ng column, yung vertical member, bibigay din niya, pati yung size ng distribution beam sa taas at platform, malalaking girder, malalaking wide plans, then you are good to go. But see to it that itong pinapatungan niya na concrete pad, i-design mo rin. Kasi may mga punching, maliit lang yung leg na yan, napakalakas ng mga forces na yan. So kailangan i-design mo yung concrete pad in such a way that it will withstand the leg reactions. So using a finite element, mas madali siya kasi ma-predict mo kaagad yung kung saan yung maximum stress na makikita mo yung kulay by merely looking at the color, and then you have some code requirements like serviceability limit state, using allowables, so mga reduction factor ng FC prime mo against kasi concrete yan eh. So masyadong maliit ang reduction, malaki ang reduction factor niya kasi hindi masyado magaling ang concrete sa ductility, hindi siya masyado ductile. The only thing na nakapag-ductile ng concrete is yung reinforcement na steel bar. But the finite element is very good to use when the material is steel, kasi ductile yung in terms of yung principle ng finite element na distortion energy that bone miss, ito yung bone miss stresses. So madali, makukuha mo na, ito yung thickness ng pad, sasabihin ng computer, kaya pala, hindi mabiak, so makukuha mo na yung thickness ng pad. So sure ka, hindi ka na masyadong economical ka kasi yung iba, factor of ignorance, napakakapal. You use so much thick pad para masigurado na hindi mag-fail, hindi magkaroon ng failure ng punching. So those are the simple stages sa designing a shoring tower. These are the simple components. Pero the basic principle, like the prediction of using the right loading, the load path chains, and then load combination like seismic and wind load, incorporate mo yan lahat. So ito naman, pinakita ko to kasi ito yung tinatawag na lifting frame. Kasi itong girder na to, ito yung ipapatong doon sa shoring tower, steel box girder. Pero bago mo maipatong siya, kailangan ka ng lifting frame. Yung iba, naka-lifting lug lang diretso, ipipick niya na dyan. But the problem of using lifting lug is the local failure masyadong concentrated sa top plans ng steel girder. So magkakaroon siya ng magkakaroon ng local failure, mapupunit yung kasi manipis lang yung steel. So nag-resolve ako ng design na I will use the lifting frame system. So nakasinturon siya. So in that way, prevented yung may beam kasi ilalim, prevented yung local failure mostly if you use lifting lug na ganito. Ito yung lifting lug eh. Pero may lifting lug ka pa rin, pero nasa lifting frame na siya, hindi na doon sa nakadikit sa steel girder. So using finite element again, you can predict the stresses. So malalaman mo hindi siya magpi-fail, pero hindi mo pa masiguro kahit perfect na yung finite element or sa tingin mo masyadong okay na yung loading, if you see that all the loads are being accounted, and then the software tells you that the expected total weight, kasi i-check mo yan manually, ang weight na niya, makukuha mo yung weight na yan. Halimbawa, ang weight nitong girder is 100 tons. I-distribute mo dito sa mga sling na yan, expected na ang reaction dapat niyan is 100 tons. 50-50 each or less than 40-60. So, depende, hindi ma-perfect yan na mag-balance eh. Kasi curvilinear yung So, here, dinidesign din natin yung pin, yung itong bolt na yan na napakalaki. Mag-isa lang yan. Natatakot yung supervisor ng yung sa project manager kasi baka maputol yan. Paano kung naputol yung isang na yan? So mahuhulog siya at catastrophic kasi nasa live traffic. So in that way, para mawala yung takot ng designer, mawala yung takot namin, nagkakaroon kami ng tinatawag na single simple performance-based na testing by using yung load test. Ibibitin namin tong nakabitin tong ng ilang oras para ma-check namin bago namin ililip talaga doon sa taas na tower. Ililip muna namin siya ng mga 2 meter high, tapos naka-area siya ng ilang oras. And then pag walang crack, check namin, ibaba namin. Then you will see if there's distortion or cracks or whatever warping of the members, then you are good to go. You are safe to beat that one. So that's one way of checking. Kasi hindi natin ma-predict kahit perfect na yung, kahit sa tingin mo, you have all the powerful tools, but still, you need to make a load test. Kasi sa procedure ng company, everything has to be certified. So, kumuha ng third party, sinertify to, binigyan ng SWL, the safe working load, hindi ka maglampas yan, so ganon. So that's the right and correct proper way in giving certification that lifting frame is only up to that capacity. So here is the yung makikita mo na naka-model yan sa SketchUp, pero ito yung nangyayari talaga sa taas. Ito yung lifting frame, nilagay yung meron siyang yoke. I-yoke mo yung sa taas kasi pag ilagay mo to, it's curvilinear, matutumba yan parang mag-twist siya. So kailangan pigilan mo sa stable siya sa taas to make it in place kasi darating na naman yung next segment na idudugtong na naman siya using splice bolts. So those are the things na titingnan natin tingin natin simple lang, pero lahat is being coordinated and being planned. Like the temporary works procedure being in place, all the permits, all the hold points. So para maiwasan ang catastrophic result or accident, mishaps. So that ends with the shoring tower, and let me just continue with this almost short exercise. So this is an exercise of moving load on a balance cantilever. Makikita mo yung launching gantry na yan yung popular na ginagamit natin sa mga railway project na may segmental, bibit-bitin yung mga segments, tapos itong kulay yellow na to magmo-move yan siya, itong gantry na yan. Ito naka-steady, ito naka-move dun sa next na pier, ito mag-move yan, and then extend na naman doon hanggang sa matapos niya yung ilang pier segment. So yan yung pinaka-effective kasi especially when you are dealing with the heavy live traffic. Okay lang kung nasa bundok ka, wala talagang structure, but in live traffic like here in Metro Manila, if you construct railway, this method is very powerful kasi hindi ka na ilalagay lang yung mga segment sa baba, ikukunin na nung suspender dito, tapos lalagyan diyan hanggang sa mabuo, lagay yung mag-post tension siya, tapos mag-pour na ng mabuo yung segment. So next na naman magmo-move na naman siya hanggang makumpleto. So it's a very powerful tool. So now the exercise here's an exercise actual to kasi ang weight ng launching gantry nito is 420 tons. Ang problem kasi is pag nasa ilog ka, yung next pier na to, halimbawa, imagine that here is a river here, may river dito. Hindi ka pwede makatawid ng kailangan kang gumawa ng tulay sa baba para makatawid yung mga equipment mo at saka yung segment mo. At saka makalagay ka ng segment dito. So, may mga method na they will complete the entire span. Then after completing the entire span, they will have that another transporter sa taas. Bibit-bitin nila yung mga segment, tapos ipatakbo nila sa balance cantilever span. And in that way, tatakbo siya doon, tapos dito na naman niya parang i-transport lang niya dito kasi hindi ka makatawid. Kasi kung tatawid ka dito, pupunta ka pa na napakalayong road, then the time is, yung element ng time talaga mawawala. So, maraming method na gagawin. So, in this case, this exercise will tell you that paano, kung kaya ba na idaan natin yung mga mabibigat na transporter. So, it's to shorten the time of launching. Itong example na to is, in the absence of permanent design, kasi hindi talaga nakuha yung permanent design ng railway, ang ginawa namin is, nag-back substitution ang ginawa namin. Ang ginawa ko na design is, kinuha ko yung dalawang 32-ton na axle na railway track, dalawang tren, magkasalubong siya or magkasabay, yan yung maximum load niya. Then ang effect ng seismic, kahit maliit lang na 15% lang na effect ng seismic, and then i-compare mo siya sa kung tatakbo, yan yung dalawang tren i-compare mo siya sa may moving load ng transporter or ito tatakbo siya ng iganon mo siya sa taas. But in this case, hindi naman to naka-design na itakbo mo din tatlo kasi peer to peer yung paa niya. But we managed to use this loading because we want to know that if this segmental box girder can carry on a heavy transport system that will run on top. So here, kinuha lang namin yung uniform load ng yung self weight ng gantry, then convert mo. Yung sinabi ko nga, naka-continuous siya sa span na 80. This is 80 meters. The span na tatawirin niya is 100 meter yung pinakamahaba, so may 20 na sobra. Ito na yung reaction ng kung tatlong leg ang halimbawa tatlong mga may gulong, PMT or straddler carrier, may mga gulong yan. Then the distribution of reaction is 262 sa gitna, ito 78. Ibig sabihin 62% ang i-carry ng gitna, 19 lang dun sa magkadulo. So yan ang worst case na mangyayari, ito talaga yung i-predict mo. Pag nailagay yan sa gitna talaga ng span, expected na yung maximum moment niya. Kasi napakabigat yung niya yan yung reaction na yan. So here I made some yung ilang position, ilang increment yan. A 10-meter increment, tatakbo yung loading na yon na 242 sa baba, gitna. Tatakbo isa sa span mo. Pagtakbo niya yan, lahat i-account niya, pati yung noise barrier increment kasi may i-construct ng noise barrier bawat while the bridge is ongoing, construct din yung barrier, dapat i-account mo rin yung weight na yon. So 10 meter simultaneous on 3 spans, tatakbo yung yung launching gantry. So ito na yung influence line mangyayari. Ito yung mga niya. Ito yung loading niya mangyayari. So until the 7th increment. So ito na yung result. Ito na yung shear diagram with those increments. So ito yung influence line. This is the shear envelope. Ang gagamitin mo sa staad, magbibigay ang computer ng shear envelope, makukuha niya yung pinakamalaking effect na shear. Saan yun? Dito mo makukuha itong dalawang pula. Itong load case na yan, yung shear na yan, diyan mo makukuha yung kung nakipapat yung nasa gitna mo na reaction sa pinakamalapit na support sa gitna, yun na pinamakalakas na shear. So nakikita mo, tinuro niya, and then alam mo na yung malakas na shear, which is ang value niya is nakalagay dyan for takpan kasi sa natakpan sa so the value of the shear, ito yung nakalagay. Ito yung maximum na makikita natin in terms of tons, metric tons yan. Then next, moment diagram naman, magbibigay na naman ng influence line or moment envelope. Lahat talaga yan, walang you will consider everything. Pagtakbo nung na yan, ng gantry na yan sa span na balance cantilever, magkakaroon ng magkaibang moment envelope. Tapos magbibigay naman siya ng maximum moment. So yan, bakit dalawang beses ng ganyan? Kasi dalawang yan lilipat kasi yung malaking reaction sa gitna dito na naman sa side. So dalawa yung pero pareho lang ang magnitude, pareho ang value ng moment. So yung comparison yun, dalawang trend na magkasabay, tatakbo yung dalawa. Ibig sabihin, kung kaya nung design niya ng dalawang trend tatakbo, tapos mas malaki ang effect ng dalawang trend na yan, ibig sabihin, okay yung ipatakbo mo yung mga mabibigay na heavy transporter kasi ang base ng design natin kasi in the absence of design nga itong dalawang train lang na tatakbo magkasabay yung weight na yan na 32 ton per axle na train, then ibig sabihin kakayanin ng kakayanin ng transporter na ipatakbo mo doon. So that's the basis of comparison sa paano kinuha natin yung lahat ng loading, weight ng itong railway ng NSCR, ito yung sa Japan to galing ng mga loading. Itong lang iba, sinold ko lang to, pero mostly itong truckload, itong sa Japanese ano yan, sa kanilang data. So makukuha natin 1, 2, 3, 4, 5, 6, 7, mga 10 yata yung isang train na yan. So isang train, 10 car. So makukuha mo lahat yung weight. Ang design naman yan is puno talaga ng tao, yung dalawa. Lahat ng train na yan, i-assume mo punong-puno ng tao, may nakatayo pa, tapos dalawang ganyan magkasabay or magkasalubong, yan yung worst case na mangyayari. And then, yan, makompare mo na siya. Ayaw mo, yan. Yan yung car. So, 8 car. Normally, yan yung standard ng railway. So, 8 car. So, tatakbo yan, 8 cars per train. Magkakaroon na siya ng shear and moment envelope na naman. Ito yung 2 railway track. Yung ngayon, yung pinatakbo natin dalawang train. Ito yung maximum shear niya. Makukuha dito, 586 tons. And the maximum moment is 5,940 tons based ng dalawang train na nakatakbo. Kasali na yung mga loading niya, mga dead loads, superimposed loads like barriers, plinths, and everything. So, yan yung loading. Nakukuha mo yung maximum moment at saka shear. Then, yung shear envelope niya, base kasi ito yung makikita mo, tatakbo siya. Ito yung train. Sa unang posisyon, ito lang. Hindi pa nakapasok lahat hanggang sa makapasok na lahat yung katawan ng train doon sa span. Yung maximum moment mangyayari sa itong posisyon na to. So, ito yung maximum moment nangyayari sa posisyon na to. Nakukuha natin ang maximum moment envelope. Yun ang pinaka-importante kasi yun ang compare natin sa mga transporter at saka lansing gantry na tatawid. Kasi ito yung original design. Ibig sabihin, kung malaki masyado itong original design, ibig sabihin, papasa yun kung mas maliit yun. Pero kung mas malaki masyado yung LG, at saka yung LG na yung pag-cross, yung 3 leg na reaction, ibig sabihin, bawal, hindi kayanin, masisira yung girder mo, yung span. So, this one, palabas na siya, kasi dito, nakaakyat na, palabas na yung train. Yan, hanggang sa mawawala na siya. Yan. So, ito yung influence line ng envelope ng shear and moment using yung supposition na yon ng train. Yan. May maximum siya. So, ngayon, i-compare natin ang conclusion. Conclusion is, yung exercise, yung LG420 to cross the BC span, ang shear envelope na maximum na nakukuha natin kanina, na 344, against yung 2-track na design, original design ng Japanese, 587 versus 344, ibig sabihin, mas maliit yung 344. So, ang conclusion, pwedeng ipatawid. Kasi malaki yung design. Pero kung baliktad yan, ito yung 587 nandyan, ito yung mas maliit, bawal itawid. Ito naman, sa moment naman, malaki yung exercise 2 railway track, maliit yung LG, yung lansing gantry na 420 to cross BC span, then you can conclude that you will allow heavy transporting on the segmental girder on top until up to the maximum reaction of around 262 tons. Yung kanina, let me go back, wait. It's very heavy. The reaction is very heavy. It's around 262.5 tons. Walang ganyan kabigat na truck kasi ang ASCO H20, yung isal niya, yung actual load niya sa gitna, nasa lang, 145 kilonewton or 15 tons. Kaya nga yung mga bridge rating natin, load capacity ng bridge, 15 tons, 20 tons. Pero ito, 262. So that's the beauty of using this simple exercise to conclude. So that ends my presentation. I hope you will reserve your questions after the next speaker. Thank you.
Thank you, Engineer Mamoko. So, ladies and gentlemen, we will now proceed with our next guest speaker, With this, may we call on life-changing President Dr. Andy Alcantara of Rotary Club of Manila Metro to introduce the second speaker.
Hi, thank you, Mark. So we can have a short restroom break before we proceed to the next speaker. Yeah. Let's have a two minutes break. Yung mga gusto pong mag-CR or uminom ng water or mag-coffee. Yeah. Before we proceed to our next speaker. Thank you.
Okay, guys, we will have a 2-minute break. So we will wait for your return after your break. Thank you.
Hi, Alric. Can you unmute LCP?
Sir Andy.
Kindly unmute LCP Andy. Alric, please unmute LCP Andy. Thank you.
Ayan, okay na. Nag-feedback. Siguro, okay na. Ayan. Good evening, everyone. Thank you very much, Mark. Past District Governor Josie Yang, dignitaries present from the Rotary District 3810, headed by Chief of Staff Dr. Vilma Binduan, my life-changing presidents, classmates, guests, friends, good evening. My task tonight is to introduce the second speaker of today's webinar, sponsored by Grid Lines and the Rotary Club of Manila San Miguel. And we are privileged to be given the opportunity to co-host in today's webinar entitled Hard Hat Sessions, Lecture 4, Design and Engineering Enhancement Program. Our second speaker is a licensed civil and structural engineer registered in the Philippines, graduated from the Ateneo de Davao University in 2002. In the same year, he successfully taught the board exam and licensure examination for civil engineers in the Philippines. He is also a chartered professional engineer, a registered international professional engineer, and an APEC engineer. He has worked with local and international engineering consultants in the Philippines and the United States of America in the field of seismic design of small to large scale projects such as high rises and wide sprawling supermalls. He founded iStructures Engineers in 2013 in Davao City and relocated to New Zealand, where he has gained further excellent and world-class experience in seismic design and assessment of existing buildings and designs of new buildings located in high seismic areas. Engineer Valencia completed his Master of Engineering Studies in Earthquake Engineering in the University of Canterbury in New Zealand. He has wide experience in the design and assessment of buildings for earthquake loadings and specializes in low damage seismic design and resilient-based design of buildings against earthquakes. He has also presented several technical papers regarding increased resiliency of buildings against earthquakes. Now, Engineer Valencia is leading iStructures Engineers to pioneer the design of buildings in Davao City, considering increased resiliency against earthquakes. He has gained a combined 19 years of professional design experience in the Philippines, United States of America, and New Zealand, where high seismic zone is a common denominator among these countries. His professional affiliations includes Philippine Institute of Civil Engineers. He is a life member. Philippine Professional Regulations Commission, licensed civil engineer. Structural Engineers Association of Davao, member. Chartered Professional Engineer. Chartered Member of Engineering New Zealand. International Professional Engineer, APEC Engineer, Structural Engineering Society of New Zealand member, New Zealand Society for Earthquake Engineering, and Structural Engineers Association of California, which he is a member. Ladies and gentlemen, without further ado, let me introduce to you our next speaker, Engineer Jose Carlos Valencia II.
Thank you for the sobrang namang introduction. But yeah, thank you very much for introducing, and I want to thank you also for having the opportunity to present present and to this webinar, for considering me to present to this webinar. But I will just jump right onto the presentation. I'll just try to share my screen. Can you see my screen?
Yes.
Okay,
Yes.
thank you. So yeah, welcome to this webinar for to this topic, the next generation of low damage and seismic resilient structures. I chose this topic because I was informed that most of the audience will be our next generation engineers. I believe everybody are still on their probably later on the latter part of their academics, and probably yung iba is in the early stage of their career. And I guess meron din namang yung mga already in the season time already of their profession. So the order of my presentation is basically I would like to introduce first, or probably discuss first, the overview of the need of why do we need a low damage and resilient structural systems, and a little bit overview of structural dynamics, because later on for these items 3 and 4, which we will be discussing next session, because for now we will only have another probably only an hour left or less. We will not be able to tackle all the 4 elements in 1 hour. So I will tackle more of items 1 and 2 tonight, and then we'll go from there, and then we'll continue with 3 and 4 on the next session. So I think for the first 2 parts, this 1 and 2 might probably purely blah blah blah, or maybe not so with the numbers. It's more of concepts, principles in presenting that. But there are many information bombs too, that you can get here, I believe. And to wrap up this 1, 2, 3, 4, this is kind of like a 5-year engineering degree plus masters in less than 2 hours. So just sit back, relax, and fasten your seatbelts. So I would like to start with this one. I think everyone already is aware of what is this. It's the ring of fire. Everyone knows this, right? So I don't want to tackle much about this one, but this is the area where most of majority of the earthquakes around the world happens. So in this area, so there are countries which is heavily affected by this ground shaking activity. There's our country, Philippines. There's the United States. There's in the South American countries as well. New Zealand and Indonesia is there as well. So with this ring of fire, there are plate boundaries, what we call plate boundaries, that are subducting each other. So this is how they look. So in our country, this is the Philippine plate. We have what we call tectonic plates. So Philippine plate is subducting under that Eurasian plate, and so I would like to talk about a little bit of what's going on in the subduction zone, or in that area, where 2 plates are moving to each other. So sometimes and there are times that they interlock, they move and interlock and release the energy, which sometimes causes a major earthquake, and sometimes just cause a what they call slow sleep event. A slow sleep event is like similar to an earthquake, but releasing the ground movement in longer periods, like weeks, months. And in the upper part of the subduction zone, yeah, the upper part, if you can see my pointer, the upper part of that one that's where we call the seismogenic depth. This is where like the behavior of the ground there is more of like a brittle, and the ones at the lower area is it's like a hot. That's the temperature. The temperature in that depth is hotter. So the ground, the soil behavior, that is sometimes what we call like a ductile behavior. So they can just move past each other. So just to clearly illustrate that, I will show you a short video of what I have just presented, just to encapsulate that one more clearly. Can you hear the audio of the video?
No.
No, okay. I will try to play it again, but
Sir, there is no sound.
there's still no sound. Okay. I'm just looking for a control how to share the sound.
Sir, you can click the share sound sa may baba ng video.
So is it dito lang ba sa ano? I
Yung
can,
button dyan, sir, yung share sound.
hold on, in-stop ko muna siya. Hinahanap ko lang yung
Tatlong button sa taas dapat. Assist na naman. Assist na lang.
saglit ha. Hindi ko makita eh. Baka na-cover lang ng another window.
Sir, sa may share video, may button din dyan na share sound.
Yun, nakita ko na. Yes. Okay. Thank you. Share sound. Apologies ha. Hindi ako masyado techy. But let
the time the What is a slow slip event? In New Zealand, the Pacific and Australian tectonic
yan, may audio na ba?
Yes, sir.
Okay, we will continue.
plates meet along a series of major fault lines. In the North Island, the Pacific Plate dives or subducts westward beneath the North Island's east coast along the Hikurangi Trough. It forms New Zealand's largest and most active fault, the Hikurangi Subduction Zone. The plates move towards each other along this fault. In the deepest parts of the Hikurangi Subduction Zone, the rocks are hotter and the plates can move past each other slowly and continuously. But at shallower depths, the plates are more brittle, and the friction between them causes them to temporarily lock together. Over time, the stress at the locked zone builds up. Every few years, the plates temporarily become unstuck and a slow slip event occurs. This releases the built-up stress and the Earth's crust rebounds. A slow slip event is like an earthquake because energy is released along a fault line, but this energy is released over weeks to months during a slow slip event, unlike an earthquake which lasts only a few seconds. You can see from the GPS sites how the land moves. Earthquakes on the subduction zone. Sometimes the movements between the plates aren't slow but sudden and fast, resulting in damaging earthquakes. Large earthquakes can occur on the subduction zone after the plates have been locked together for a long time, perhaps for hundreds or even thousands of years. Over many years of locking, enough stress and pressure builds up on the fault that eventually the fault breaks, allowing the plates to suddenly slip past each other in an earthquake. Can a slow slip event cause a major earthquake? Slow slip events often occur next to the parts of the plate boundary where earthquakes occur. Scientists are investigating how a slow slip event can increase stress on the locked segment of the plate boundary and whether or not this can influence the timing of future earthquake ruptures. Once scientists can better understand this relationship between slow slip events and earthquakes, we might be able to use slow slip events for better earthquake forecasting in the future. However, it's important to know that we have observed dozens of slow slip events in New Zealand that have not triggered large earthquakes. Researching slow slip events in New Zealand. Studying slow slip events could tell us a lot about how and why New Zealand's biggest earthquakes occur. GNS Science geophysicists are working with other international researchers to resolve where slow slip events happen and what effect they have on the plate boundary fault. Here you can see a large locked zone covering much of the central and lower North Island. This locked zone is where pressure and stress are currently building up that could be relieved in a future earthquake. Next to it is a slow slip zone, and then next to that is a steadily creeping zone. GNS Science is involved in several large international projects to investigate the causes of slow slip and locking on the subduction zone in New Zealand, because the Hikurangi plate boundary has shallower slow slip events than elsewhere in the world, making it the best place globally to undertake this research.
Okay, so thank you for watching that one. Hopefully it gives a little bit of more information on what I have mentioned earlier about subduction zones. But yeah, before I would like to continue, just a quick mind twister, like if with this question. So if there's a fault line circumferencing the Earth, what magnitude of earthquake is required to rupture the circumference of the Earth? So assuming that there's that values of ground properties are there, what do you think? What do you think would be the magnitude that will be? Like, just take note that those fault lines that we know that we have probably in the field books are only in the range of the length of those fault lines are in the range of 100 to like 1,000 kilometer long. Like I think the San Andreas fault is I think a 1,200 kilometer long fault line. So I think it, and if I'm not mistaken, I think it's the longest fault line in the world. So referencing to the usual magnitude number that we hear like 7, 8, but that's only around like 100 or 400-kilometer long fault line. But for this one, assuming that the fault line is across the circumference, so what number you think would be? You can chat. You can put your number there in the chat box. Would it be 20? What magnitude 20? 100? What do you think? Just take note. It's not a although it's not a linear relation. It's not a linear relationship between magnitudes and fault lines. It's more of like exponential or logarithmic. So, well, just to further proceed, yeah, there's someone mentioned 10.5. Yes, you're right, correct there. So that's 10.5. So ni-round off ko na lang to sa 10.6. So given those assumptions, which are not unrealistic, so we would expect that a magnitude of 10.6 event would rupture the circumference of the Earth. Oh, good, well done, well done. However, it is not really the value. It's not really the magnitude value that we are using to design buildings. It is the peak ground acceleration. That's what shakes our that's what shakes our building, because the ground surface shakes because of these ruptures in the ground, and it vibrates towards the surface of the Earth. And our structures are constructed on the surface of the Earth, and that vibrates, which creates a ground acceleration, and that ground acceleration will be absorbed by our building, and then the energy will be released as well by the building. So it's not really the magnitude value. So let's say sometimes it's siguro meron kayong naririnig na this building is designed to up to magnitude 10, magnitude 8. But really, sometimes a high magnitude can have either a low or high PGA. So it's not about magnitude. It's about more specifically with the peak ground acceleration. Magnitude is more of like the size of the earthquake, the energy released from the earthquake. That is more of what the magnitude means. The meaning of magnitude is. In the NSCP code, you can see earthquake zones. In the Philippines is divided in 2 earthquake zones, which is the zone 2 and zone 4. Yeah, this represents that structures on those zones will be designed using a PGA for the zone 2 PGA, peak ground acceleration of 0.2, and for zone 4 peak ground acceleration of 0.4. So the code does not say this structure here is designed using a magnitude value of 7. No, it's not. The magnitude there in an NSCP code is used to categorize the different types of fault lines, like fault line A, type A. Sorry, type A is a fault lines that are able to produce magnitudes of 7 and above, like that. But the peak ground acceleration is fixed at 0.2 and 0.4. The code does not although the code does not directly explains this, but that's why for some they just use this directly without deeper understanding. Why I would like to talk about this first in the context of a low damage and seismic resilience, because I want you to understand first really about earthquakes, how earthquakes happen and how it shakes our building. what's the probably the overview of the properties of it. It's better to understand the cause of that shaking to our building, and then later on we will move forward. How does our structure respond to that ground shaking? So we also, in terms of the levels of earthquake, it's better to quantify it as there's a better quantification of that, which is used internationally, like the 500-year earthquake and the 2,500-year earthquake. That's how the levels of earthquake are categorized. Like on a global consensus, what is 500-year earthquake? This is an earthquake that is on a probability context. This is an earthquake that has a 10% exceedance in 50 years with a point ground acceleration, with a peak ground acceleration of 0.4. So as what Engineer Arthur mentioned also earlier, like we are not perfect. So this is always in the engineering, in the design of building, it's always in the context of probability. Even the derivation of the loads, even the derivation of those load factors you use in your load combinations, those are derived using on a probability context. So I want to just mention about design level, the term that I will use, design level earthquake. So the design level earthquake this is the earthquake that we use for a certain building, to design a certain building. So it could be the design level earthquake, it could be the 500-year earthquake, it could be also a 2,500-year earthquake. For the 2,500-year earthquake, this has a like a 2% exceedance in 50 years. So meaning, like, if we have a building which is normally the design life of our building is 50 years, but it doesn't mean that 50 years it's masisira na siya or bababa na yung performance. No, it's not the meaning of that design life. It's just the globally accepted minimum design life of a building for 50 years, that it should be durable for 50 years. You can actually, there are structures that are even designed for 100 years, like some lifeline bridges. They are depending on the jurisdiction or requirements of a certain country, of how in New Zealand, for all the bridges in New Zealand are required to have a design life of 100 years. So you design according to that. So the design level earthquake of that is higher than those structures that are the design level. The design life is only for 50 years. So the big one. So we've always heard this as well. I think everybody know what the big one is with this project. If you can see on the snapshot that I have taken, so this is a projected destructive effects. So I took this from, I think this is from the Myers. If anyone has already heard of that, I think it's a study. It's a joint study done by JICA and FIVOX to conduct a study, projected study for what if in case the big one, the big one will happen in Metro Manila. So that's the kind of the summary of what will happen. So you can see schools, 1,400 schools will be damaged. Even hospitals will collapse. Collapse of 40% of residential buildings. Residential buildings includes, of course, those condominium buildings. So it's very catastrophic. the effects if you will read it, if you'll read that, or just by this summary. But really the question is what have we been doing, or what have we done to our buildings? Earthquake drills, earthquake drills. I don't think earthquake drills will prevent the building from falling. So there are other for these effects. There also are other structures that will be affected, like bridges, our harbors and ports. But I will just focus on buildings. So this one also is another warning. Although I specifically put it here because it's an old warning. It was still August 2015. But I mean, for my opinion is we should treat this warning seriously, and proactively. So far, what are we doing to prepare against earthquakes? Like, yeah, we just do like earthquake drills. We're not doing anything to make our buildings sustainable against this earthquake. So warnings like this never really gets old. And yeah, as Miss Marcy also mentioned earlier, that yeah, earthquakes do not kill people. It's the building that will kill the people. Falling buildings or parts of a building will kill people. So I'll just bring you back to some of the past Philippine earthquakes. So what we have, I think this is the 1990 Luzon earthquake. So three-ish, 4 decades ago. The system we are using is still the same. The structural system we're using before then is still the same as what we're doing now. Although there are just a little bit of enhancement, refinements to the system, tighter detailing requirements, but still the same system. In fact, many buildings are still built non-compliance. When in Davao, yeah, there are buildings that are, you can easily see while it is being built if it's non-compliant or it's compliant. I mean, just looking on the structural system itself. But yeah, I wonder, but still being issued with building permits. So, but I will not go deeper into that as I don't want to open a big can of worms regarding that issue. So this one is another photo. So I think the one is still the left photo is from still in the 1990 Luzon, but the one on the right is from the Bohol earthquake, as 2013. So this photo I saw that yeah, you see it speaks for itself. So budget, it's budget. So that's what you get when you do budget. I mean, you have a low budget or so. If you allocate less budget on your structure, that's what you get. These are examples also of disposable buildings. I said disposable buildings, but I will talk about what's disposable buildings in a minute. So these are some buildings are once have been hit by an earthquake, a strong earthquake, you can no longer use it. For example, the one on the left, I think this is the Cebu City Medical Center. After that one was hit by I think from the 2013 Bohol earthquake. Yeah, they demolished and replaced a new one. And similar to this Gaisano Mall Center in Surigao, it was never used again. And further on, Surigao, I think this is from the Surigao earthquake. Yeah, you can see that. If you look closely on those damage, where are the plastic hinges occurred? I will talk also about in a minute what's plastic hinges. The plastic hinges in this photo is those ones. That one, that's a plastic hinge. That one as well. So you can see that the plastic hinge occur in the column. So that's a non-compliant. The code does not allow that. The code does not allow plastic hinge to occur except at the base. It's fine to have plastic hinge at the base, but not in these areas, not in those areas. You can see here, this one, the whole second floor is gone. It's gone already. So this is what happens when an engineer does not tell the structure what to do. You know, we'll come to that later as well. What that means of how to tell the structure what to do. So further on, more recent damage. I think this is the Davao earthquake last 2019. So look again on those damage, where the damages are still in the columns, and that one there. So this one, the ground floor is gone. Just take note of that mechanism. We'll discuss that as well. In here, if you can see, plastic hinge in the column, plastic hinge there, major damage in the column. So these are non-compliance, because the code does not allow plastic hinges in the columns. And that one, yeah, the ground floor is gone as well. And so the one on the right is it's a hotel in Kidapawan. You can also see that plastic hinges there. So there's the trend, right? There's the trend. The trend in this the trend on those collapses or those damaged undesirable mechanisms is because, from my just own opinion, maybe it wasn't the desired mechanism wasn't realized in the actual design. This has collapsed, but yeah, that building is still standing. So looking further into this damage, so this is an example of a plastic hinge. So that's a plastic hinge occurred already in the face of the column, but it occurred in the beam. So that's a more desirable location of the plastic hinge. And you need to tell the structure that whenever a plastic hinge needs to occur in this area, you occur there, not in the column. So another example is this one. This example here. This is a shear wall. For shear walls, the desired location of plastic hinges is at the base, and this is at the base of the ground column. The ground floor. These cracks that occur for me, that's the perfect picture of what a plastic base hinging is for a shear wall. So these plastic hinges have a desired location in a building. So as the engineer, or you as the engineer of the building, you are the one who will locate them, not the software. Not the software, not the structure. You tell the structure what to do. And these cracks, yeah, that's that one. This cracks is at the joint. This one is a crack on the slab. So later I will explain why that occurs, why the slab has elongated. And there's also these are for steel structures. So for steel structures, what we our desirable failure mechanism for steel structures is tension yielding or buckling of bracing, but not tension fracture. So we allow a little bit of buckling to attain that ductility requirement of the structure, or the ductility that we desire for the structure. But it always needs to be accompanied by something in tension. It's not all in compression. Not all braces should be directed just in compression. So if you have a compression bracing, you also need to have a tension bracing. So this one is a perfect illustration of a plastic hinge in steel structure. So the plastic hinge occurred at the beam, not at the column. This one is a plastic hinge at the base. That's okay, but you can see that the column base is already, very, very damaged. So that structure, although this one is from my test from the university, but you can see it will still support vertical loads, but the structure will no longer be able to be used again. So this is what I mean, like why that slab has teared apart. So plastic hinges, the desired location of that is at the beams. For moment frames like this, so plastic hinges at the beams at the face of the columns. So that's where the desired location of those plastic hinges. And when plastic hinges occurred, your plastic hinge will elongate a little bit. One plastic hinge will elongate a little bit, but for the whole span of the frame, if you add those elongation and this plastic hinge from there and there and here and here and there and there and there, if you add those, it will be a little bit significant if you add them. So after the earthquake, your frame will somehow look like this because it has elongated. The beam has elongated. And after the earthquake happens, so your structure will look like that. So there's a residual displacement. And since this has elongated, so that's why your floor has teared apart, has elongated as well. So that's what it means. Here, I show this one because this is an example of that base plastic hinge. So that's a plastic hinge there at your base. So after testing, moving it back and forth, after the test, there's a elongation already, longitudinal elongation of that wall. So imagine if you have a column there and you have a wall here. So after a design level earthquake, after a very strong earthquake, so your floor is no longer level. So that's what it means there. So if your floor is no longer level, so there's issue in serviceability of your building. And if your building is tilting after the earthquake, if tilting a little bit just exceeds 0.5% of the story height, that's the serviceability limit. If your building after an earthquake is leaning more than that, so it exceeds already the serviceability limit. So why earthquake resilience? Because in every earthquake there's death, there's significant damage, there's possible demolition of your building, there's downtime and disruption, and some other are calling this as 5D. In our current design philosophy, or seismic design philosophy for buildings, there is this 5D. And this 5D, all of this is a waste of money, waste of money and hindrance for continuous progress of the city. For example, if there's a city that is just progressing and then an earthquake hits that city, so, and what if most of the building will be like this? So they will go back to that city will go back to where they've been, like step one or square one. So that's a hindrance for continuous progress. So we need to be sustainable. And then recognizing the effects of natural disasters has become a major global concern. Cities surveys conducted show that a high percentage of the largest cities in the world and more than 1 billion people reside in areas that have experienced severe earthquakes, resulting to large number of casualties, which has a major challenge. That's why there's a major challenge in regional and national economy. And just imagine for example, the big one will happen in Metro Manila. And what if the big one will happen? So there's a major challenge, how there's a significant impact on the GDP or in the economy of rebuilding that regional area again. And how then can our country's public and private sector be better equipped to overcome the many challenges of recovering from such tragedy? So how do we prepare for such adversity in the future? But before that, I will just quickly explain what is resilience. So resilience is ability to recover and return to normal operation after an adversity. An adversity here is the earthquake. So normally, we spend our time during normal weekdays in office, in school, pasyal-pasyal sa mall, or if saan tayo nakatira, sa condo buildings. So our current scheme in building design, it's kind of reactive, not proactive. So duck down cover is good, but it will not save the building. The way we design buildings today is the same five decades ago, or 3 to 5 decades ago, which is just focusing on life safety performance. So possible strategies in building seismic design to attain resilience against earthquake is, of course, we need to avoid damage. And if we would be able to allow some controllable damage, so that portion there is easily repaired or easily replaceable. Like for example, if we look into your house, and you have a electrical circuit, electrical system in your house. So in electrical system, we have a fuse, right? We have a fuse. So once the electrical system is overloaded, the fuse becomes busted. So if you have like a reserve fuse somewhere in your house, then you can just remove that busted fuse and replace it with a new one, and system is up and running again. So we can, that principle or that design concept, we can extend that to buildings as well. So this is one of the goal of seismic resilience. So we need to avoid damage to the building. We need to protect also the businesses, the downtime in the businesses, the operation of those businesses. We also avoid the disruption of people's lives, right? For example, you have a high-rise condominium there, and after a strong earthquake, the building can no longer be used because it's tilting more than 0.5%, or the serviceability limit has been exceeded. So there's a disruption in people's life. Where they will go? Siyempre, hanap na naman sila ng saan sila titira for quite some time. And repairing building is not that easy, and it's not fast. In our current code requires only, our current structural code requires only to protect lives of the people as mandated by law. As life safety performance level, but not the building. The law does not care about your building. If you have a building, bahala ka dyan. Basta yung mga tao nandyan sa iyong building is safe, makalabas. The building after the earthquake, the building should still be standing to whatever extent of damage it is, and the people inside can safely go out. So yeah, the code does not protect the buildings or the businesses as well in it. So mga negosyo, bahala na kayo. So earthquake, yeah, just repeating it, this one, earthquake does not kill the people, the buildings do, but unfortunately, earthquake does not read our code. What the earthquake does is to shake your building, look for the weakest link and destroys it or damage it. So this one is from the MM Myers as well. So with these warnings, what are we doing? That's why there's a need. I mean, on my opinion, that's why there's a need for resilient buildings, no? And also, resilient and resistant are two different words. So you might encounter later on someone using, this is a resilient structure. So it takes a little bit further to make your building resilient. Complying the code minimum requirements does not make your building resilient. It makes it resistant and code compliant, but it doesn't make it resilient. You need to go a little bit further than the minimum code requirement. So nearly 2 decades ago now, yeah, from this study, the system we're using is still the same. So as mostly the young engineers, as the next generation civil engineers who will be specializing in structural engineering. So yeah, I hope you can pick up something from here and make our communities better. So with this one, this is a reinforced concrete monolithic construction for buildings. I'm just focusing more of buildings. Soon, or rather now, so this RC monolithic construction will no longer be fit for purpose. So why? It will soon become an obsolete system. So why? Because the demand of the public now is, it's getting more higher, getting more, lahat gusto now. People wants to, after an earthquake, people wants to get in the building as soon as possible. I want to get in my building now. I want to operate my business now. So with this kind of system, you cannot make now possible after a design level earthquake for this kind of system. So as what I mentioned earlier, this shear wall, base of this shear wall, has portrayed a perfect picture of what a plastic hinging on the base of a shear wall. So for me as an engineer, if you will ask me after a strong earthquake, I will tell you that there's damage, but I will tell you also that this is expected. This is an expected damage. But for non-technical people, they will not understand it. Even let's say even if this designed for designed by a very very brilliant famous engineer, as long as this one is just meeting the code minimum requirements, this will happen. But the expectation of the public is not like this. The expectation of public is they can use it. They don't care how did you design it, but what they want is they can use it after the earthquake immediately. And just to take note as well, the cost to repair this one, that wall, is twice the cost of building a new wall. So just take note of that as well. So this is just an illustrative. Hold on. Yeah, I made a model. So this is somehow a very simple SMRF, or what we call the special moment resisting frame, and how it is, how did it perform after an earthquake. there is no sound. There is no sound in this, but just look on the video. So this is a time history of a very simple two-story frame, but you can see what happened to the frame after the earthquake. It's already tilting. So there's permanent residual deformation. So to repair this frame, there will be a high cost because you need to relevel or replumb the building. So it depends on the scale of the building. So the cost of repairing that will depend on the scale of that structure. And at the same time, you will be unsure of the future performance. After another strong earthquake, will it be like this again? And it's very time consuming. Battling with insurances, it's not easy when you want your building to be repaired. So yeah, we can't make, or it's difficult to make our city sustainable against earthquake because our current design philosophy is old. This design philosophy is like five decades old already. So to move further, so this requires a paradigm shift in building design. So sustainability does not only mean that reducing impact to our community, reducing impact of our community to the environment, but also reducing impact of the environment to our community. So it's a two-way relationship. So I think you have also heard some of this one, the LEED, the EDGE, green building programs, etc. Most sustainability programs, codes, and standards focus primarily on energy, the material, water conservation, zero carbon, indoor environmental quality and impact, and site selection and development. But one thing, each of these is an important aspect of sustainable design and sustainable building design and construction. All these are important. However, the assumption that the basic building will be resilient is not inherent. It's not inherent to these programs. They tend to forget to overcome the building's public enemy number one. So building's public enemy number one is, the earthquake. So our current design practice, so this is our current design practice. So what I have mentioned earlier is you have those, I mentioned this one as 500 and this one as 2,500 just to round it up. So on a 500-year earthquake, you can see here, that's life safety. And on a if this is our design level earthquake for a particular building, so that's our life safety performance for that building. If you subject again that building to a higher level of earthquake, it should not collapse, but just about to collapse. So that graph would, which means this coloring in the graph means something like that. So your earthquake, your building and this level of earthquake. So maybe that for this representative building, maybe just that sign will fall. And this is like the design level earthquake. So cracks there, cracks here. And for our ultimate limit state, I mean the 2,500-year earthquake. So that's in the brink of collapse. So that's what we are doing on our building, the current practice that we do. But what we want, where our direction is to match, I mean to match or to keep up with a public demand is this one. So we want even those very rare earthquakes and in the design level earthquake, we want it after that earthquake happens, we want it to be still operational. So that's what they want. And that's what we need as structural engineers. That's what we need to do. Our current code says, if you want immediate occupancy, you just multiply the base year by higher importance factor. I'll show you a little bit what that means. A higher importance factor, for example, in a hospital. If you want to design a hospital, the code says that just multiply the base year by 1.5 and you're good. But that did not happen to one of the hospitals that we designed. It's not, we multiplied 1.5, but still the hospital is now it's still not being used. So that was 2019 and now it's already 2021. It will be nearly 2 years. That still is not being used because they are still repairing that hospital. So it's not immediate occupancy. So something's not right. So for the time being, this is because for the time being, current design practice and level of damage allowed by design codes is now getting unsatisfactory as compared to the public expectation. So the basic objective typical for ordinary buildings. When I say ordinary buildings, these are the offices, the malls, the condominium buildings. A life safety damage level would be considered acceptable under a design level earthquake. But I put here by who? Acceptable by who? The occupants. The occupants doesn't know anything about, especially for non-technical buyers that bought a unit in a condominium building. He doesn't know about this one. Under a design level earthquake. This means that excessive damage, sometimes beyond repairability, is the current acceptable target by the code. And with that, the building sometimes is termed as disposable building, because after a very strong earthquake, your building could be repaired for so much money, or you will be able or you will demolish and replace the building, the damaged building, with a new one. So users, building owners, developers, residents, clients, or other stakeholders of such buildings have different understanding or expectation from an earthquake-proof design. Earthquake resistant is not earthquake proof. So earthquake resistant, this is the earthquake engineering community's view, but earthquake proof, that's when you say this is a very code compliant. When someone says code compliant, when you comply with the code, it's earthquake proof. No, it's not. The current trend, especially for structures that are not owner designed, built and occupied, is to maximize profitability by simply satisfying the minimum provisions of the local building codes. When I say this, it's somehow like, for example, me, I will build a like 5-story or 10-story condominium building. Because I will not occupy the building. I will not live in that building. I'm a businessman, so I will do business. For those people that bought units there, they will not tell. They will not. Of course, they will not tell it to them that your building is disposable building when subject to a design level earthquake. So, but of course, it is a business. What businesses do is just continue to do marketing. The public will tend to forget later on, because earthquakes are not continuous, to remind everybody. But yeah, this marketing they are always there. So the performance of these condominium buildings in recent earthquakes in Davao region did not meet public expectation. Many condominium buildings there were highly damaged, and many buyers shooed away from condo building for quite some time, and now because wala na masyadong earthquake nangyari, the public tend to forget, and some bili pa rin. So this is just an example of a seismic loss assessment. So sample the aggregation of a damage from a design level earthquake of a 10-story building. So you can see when a building is subjected to a design level earthquake, you can see that the seismic loss for beam columns is 14%, for slab is 10%, and the rest is already non-structural. So structural, we can say structural is only 24% only. If you will repair the building, 24% of the repair cost will be on the structural, but others are not, does not appreciate that the rest is non-structural, which is the mas malaking share of repairing the non-structural elements. So, but with correct detailing of non-structural elements, detailed to accommodate design drifts of the structure, yeah, we can lessen that damage. And more often, because structural engineers are no longer involved in this very detailed for non-structural elements, like for example, you have a drywall partition in the building. So even this drywall partition, they would still need to be able to accommodate those drift requirements from the structure. If not, after a strong earthquake, they will be damaged as well. So you need to repair those. So increased resilience is not really only for structural, but it's the entire building system. So it's not only for structural engineers, but also for other trades as well, like the architectural space, the electrical, and the mechanical. So they are involved in this goal to attain a high increased resiliency of the structure. But one thing to note, by protecting this one, your 24%, you protect the rest. You protect the rest. But losing this one, losing the 24%, you lose everything. So just put that in the back of your head. So with this damage, let's just a little bit quantify. So types of damage, we have this structural damage, which is related to member strains, to ductility demands, non-structural damage, so yeah, related to structural interstory drifts, and the content damage are related to your story acceleration. So this is what I mentioned earlier. So this is the desired more for moment frames. This is a desired global failure mechanism. This is not a desired global failure mechanism. This mechanism has been I showed on one of the damaged building I showed you, this has portrayed that mechanism. And yeah, with this mechanism, the ground floor is gone on that building. So what's the challenge? The challenge is to reduce all three at the same time. Reduce structural damage, reduce non-structural, and reduce content damage. So that's the challenge. So is this possible? So no, it's not with conventional systems, but it is possible with low damage and seismic resilient systems. So the acceptable damage, I've discussed that earlier, at least to the non-risk takers. So resilience now has become a major concern in seismic design of buildings. So in here, the big question really is you might ask yourself, what is really the design philosophy? The big question is really the ductility. This is the design philosophy of current design practice to achieve life safety performance, and can at the same time assure operational performance of building following a design level earthquake. No, it's not. Operational performance is attained through avoiding damage, as what we discussed earlier. So in other words, avoiding use of ductility to structural members' inherent properties. That's what we need. So because ductility is damaged, but if we can provide ductility to the building, without so much damage or with little damage, that would be better, because the structure will dissipate energy more efficiently, and at the same time you can use it. You can use the building right after the earthquake. So in our base shear formula in NSCP, so you may probably wonder what that R value is. So remembering R value or R factor from NSCP. So this R means that it allows the building to be damaged to survive the earthquake, because it needs to dissipate the energy from the earthquake. This is a trade-off between economy and safety. So take note that avoid using moving forward with design of buildings to increase resiliency. We need to avoid using structural members' inherent properties as a source of ductility. So what is the R factor? So the R factor is the response modification factor, and we'll discuss that a little bit later. So there's that trade-off there. So ductility, so that's ductility equals damage, and damage equals repair or demolish. So structures designed in accordance with even the most modern building codes, so not only in the Philippines, but even in New Zealand and in the US as well. If they just follow minimum requirement, following the minimum requirement, are expected to sustain damage during a design level earthquake when using traditional systems. So these are traditional systems. Now, monolithic beam column joint, monolithic special moment resisting frames. So that's it. So buildings are normally designed, so we've discussed it earlier, but research says that buildings will experience at least once in its life a design level earthquake. So there's a high percentage that if you're building, if you use a traditional system and your building will experience a design level earthquake within its 50-year design life. We don't know when in that 50-year design life. It could be your building is completed now. It could be the day after or the hour after. So we don't know. Or 49 years later, we don't know. So as long as it's within the 50-year design life. So what we need is, even that design level earthquake comes, our building will stay intact. So this is an example of a building. This is a building in Christchurch, New Zealand. This is a building, I think a 25-story building or 20-story building, the Grand Chancellor Hotel. So after the strong earthquake, by the way, the earthquake in here is I mean, the peak ground acceleration of the earthquake that happened in the city is higher than what the buildings were designed for. So after the earthquake, the building is tilting, so it's no longer used. So they demolished this. They demolished this. They demolished this building. Another building. So ductility. So this building, if you can see on the left, after the earthquake, it looks fine. It looks all good. It looks still can be used. But if you look closely, after the assessment of these buildings, a lot of plastic hinges occurred already in this portion. The desired failure mechanism has been realized for this building perfectly. So no column hinging in the columns. All hinges are in the beams. So, but after the structural assessment, the cost of repair is almost equal to building a new one. So that's why this building was considered like a disposable, and they build a new one. So another one, this is a police headquarters. This is an essential structure, an essential building. This has been designed with a higher importance factor, but still they need to demolish the building. Another one, this one, same story. I just want you to have a look on, because of what happened to Christchurch, the epicenter was really close to the to the city center. So the city was really hammered during that earthquake. So this is the city before the earthquake, and that is the city after the earthquake. So a lot of, if you can see, a lot of demolished buildings already, and some of these are still about to be demolished. Those area there. So that's what happens here, and it takes I forgot the percentage of the effect. I mean the economic effect of rebuilding the city, but it costs a significant percentage on their GDP to reconstruct the city. So before the earthquake, so just looking further before the earthquake, that's the buildings there. So after the earthquake, that's what happens. Buildings have been cleared already. So there's a lot of disposable buildings there. So why do we say disposable buildings? Because the building is designed to protect the lives of the occupants at the time of the earthquake as life safety performance only. In a design level earthquake. So this happens only once. So now we cannot afford to demolish a building because it just did what it was intended to do. And your building is only designed for one strong earthquake if you're using a conventional system. So our current code says if you design the building to have an immediate occupancy, you just increase by 1.5 for essential facility, and yeah, that's it. But from this research, they said that it was concluded that high safety cannot be achieved simply by increasing seismic coefficient of structures. So something's not right over here. If you can see, this building survived. Yeah, I think this one survived 3 strong consecutive earthquakes. But where is the immediate occupancy with this one? No, there's no immediate occupancy with this one. Until now, it's not being occupied. Repair is still ongoing. So buildings with extreme residual drifts, so that's becomes unserviceable and could no longer be occupied. The building may either be repaired, demolished, or rebuilt. Repair can be expensive and time consuming. So in short, your building may be potential for a candidate to be a disposable building after a major earthquake. And period of reconstruction and repair involves time element attended with various complexities that could relate to, for a business, significant financial loss, loss of investment and property. If let's say your building is only, let's say 5 years old or 3 years old, and then a strong earthquake happens, and it gives potential disputes with insurance companies. At the moment, I have spoken with a few insurance companies. And they're not yet aware of these resilient systems, no. But I think with resilient systems, they're not still aware of this and how the concept of building design works. But later on, if they are already aware of this, there will be a lot of potential disputes that I can foresee with insurance companies. Because if your building collapses on an earthquake with peak ground acceleration less than the 0.4, let's say your building is in zone 4, with a peak ground acceleration of less than 0.4 and your building collapses. No, the insurance companies, from my point of view, the insurance companies will not cover or insure or pay you for the repair or for the reconstruction of your building. Why? Because in their policy wording, that all steps have been taken in accordance with the National Structural Code of the Philippines. So if your building has been non-compliant, and then you construct the building, and then it collapses on an earthquake, which is an earthquake with a PGA of less than 0.4 on a zone 4 area, they will use that against you. because they can also hire, the owner can hire engineers to do the assessment, and the insurance companies can hire also their structural engineer to do some assessment in their favor. So that would be the potential disputes that I can see. So yeah, unemployment, we've discussed that. Disruption to economy, we've discussed that as well. So awareness is really the key, like what we are, like what we are doing now. So increase the level of communication, just like what we are doing now, raising the bar, help to, educate the non-technical people to a level they understand, or shall we say layman's term. They cannot understand numbers, those non-technical people, but they can understand images, figures. So you need to show them that. So what can we do? So these are the systems that we can use to increase the resiliency of our structure. I will just go over quickly with this one. So the characteristics of a low damage system is it suppresses structural damage. So no plastic hinges. So member replaceability. So very easy to replace that one. If that is damaged, you just unbolt and replace it. And there's a self-centering capability. I will explain it later. What's a self-centering capability means. And suppresses floor damage. We don't want those damage. We don't want those elongation, frame elongation. So just to move forward, I forgot the time I started, Ma'am. Do I still have, how many minutes do I have left? Sir Rex, you are there? How many minutes do I have left?
Hi, sir. Gaano po katagal yung slide niyo, sir? Pero we actually 10 na po eh. Pero kung konti na lang naman, can still continue, sir. So we can proceed.
Okay, maybe I'll just quickly go over within 5 or 10 minutes. Is that all right?
Okay, sir. Yeah, 5 minutes, 5 to 10 is. Then we'll proceed with the awarding.
Yeah. Okay. Thank you.
Thank
So with this one, this is just the review of the structural dynamics. It's a 5-year engineering degree in few minutes. So bear with me. I'll try to be as understandable as can be, but it will be fast. So for simple buildings, so every building, we can model it like this. We can represent it as a lollipop. I call it lollipop structure. So that's what we call the single degree of freedom model. So for seismic load path in a building, so that's the earthquake, that's the ground shakes, so that's the soil, effect of the soil, and that shaking goes through the foundation, vertical elements to the diaphragm. The diaphragm is our floors, our story. And from the diaphragm, it goes back to our vertical elements, down to the foundation and down to the ground. So that's our basic seismic load path in a building, building response path. So simple model like this. So I think this is still for those ones that are nearly graduating. I think this is still fresh in your mind from your structural dynamics. So I will not tackle much more of that. This one as well is just similar. So earthquake ground motion. So I'm just tackling here how it is being recorded. So the structural response, we have that ground motion, and then we have that lollipop there with that structural properties. We have that period, we have the dumping. So, and response may mean any quantity of interest. It could be deformation, acceleration, or velocity. And the structural response, if we have that ground motion, we have our structure here, which is, let's say that's a period of 1 second and a dumping of, let's say 2%. So if you will perform a dynamic analysis, you will get this one. That's the response, that's the displacement response of the mass, of that mass, and that's the acceleration response of that mass. So response spectrum, the reason why I want to tackle with the response spectrum, because we will also be dealing with this one when we get to those resilient systems, because they will be, because you can quantify resilient systems easily with just the ADRS, what we call the acceleration demand response spectrum. So with this one, what you have done in here, for example, that ground motion, you will plot the maximum, you will plot the displacement, and you get the maximum response, and another maximum response, which is that one. So you repeat this exercise for different values of natural period. So you reiterate that one with 1 second, 1.1, 1.2. You will get this curve. That's our response spectrum, and this is from the NSCP. And if our structure is so rigid, infinitely rigid, so that mass and the stiffness of this is infinity. So this mass, the peak ground, the acceleration response of this mass would be equal to the PGA, because since that is very rigid, the ground and that mass is moving the same, at the same speed, the same rate. And what if also if we have a very flexible structure where K is very less 0, but not negative. So very small stiffness, no, very small stiffness. So what is the displacement of that mass? So the displacement of that mass would be our peak ground displacement. So that's what we have discussed there, displacement and acceleration. I'm just discussing this one on two extreme ends. So by response, yeah, we'll be able to get that acceleration response, velocity response, displacement response. So you have, that's what I mentioned here. So you have 0.5 seconds, 1 second, 1.5 second. And when you plot that one, you plot with the period, and that's the displacement. And you plot that one, you will get your, what we call here, displacement response spectra. So if instead of displacement, this is displacement, instead of displacement, we will plot its acceleration. So we will have that acceleration response like that, which I will show you in this next slide. So you can make various response spectra using, that's the displacement spectra, that's the acceleration spectra. So you can easily, if you have a single degree of freedom representation, you can easily from that response spectra, you can easily see what's the elastic displacement of that mass laterally. You can easily see, you can easily identify with just having, when you just know the period of the structure, you can easily identify this structure will be displaced elastically in this range or in this amount. And in terms of acceleration, because we want to design the structure, so force, inertia force is equals to mass times acceleration. So that's our acceleration there, and this mass is moving that direction, and we will have also a force there. So you can do, you can easily get what's your base shear. You can easily get the base shear you will have at the ground. So just to have a very short example, so we have our acceleration, ground acceleration time history there, and we have this acceleration response, and you want to get the base shear. So that's for a period of 1 second, So let's say you have 1 second there. So that's 0.48 G, and the mass is 10 tons. So you have already your base shear there, and your base moment, the base moment there is that value. So you can easily plot this one. This one is similar to that example here, just expanding it a little bit. And so that's for single degree of freedom. This is for multi-story. Multi-story is somehow similar, but you have multiple masses already instead of one lump mass. So you are distributing it to different levels, and you need to do some model analysis for that one. So you have mode 1, mode 2, mode 3, and in each mode you will have period. So as what have also Engineer Arthur mentioned earlier. So after you have completed your model analysis, there's a SRSS or CQC to combine the effects and to get the building response. So that's mode 1, mode 2, mode 3. And yeah, and just by estimating the maximum response, so each mode you have a response from each mode. So that's the response of the first mode. This is the second mode, and that's the third mode. And then you combine them, and that will be your design force. Although combining them, although the modes does not happen all at the same time, but in our calculation, we just assume that in SRSS or CQC, we just assume that all the modes, for example, your acceleration here, acceleration there, acceleration there, although those acceleration does not happen all at the same time, but in the design, we just a little bit on the conservative side. And lastly, just to give you a little bit of where our base shear, because it's also important, whatever those equations written in the code, it's always better that you understand where do they come from, and it's always good that you always work back to your first principles. So first principles is this one. So we have a ground here, so the ground shakes, and that mass there shakes as well. So this is the response. So from our inertia, force of inertia, the basic equation of force of inertia is force is mass times acceleration. So that area max is divided by G. So that's the G force. So that's why we have like 0.4, 0.2, and that's the weight of the mass. And we can, assuming that's a factor C, we'll denote that as a factor of C. And we can further dissect what C is. So what C is from this expression. So that's A max over G. And we'll further dissect what A max over G is. So A max over G, this is your spectral response factor. Your spectral response factor, spectral shape factor. That's the factor that shapes your response spectrum. So that's that spectral shape. It's a function of your soil type and the Na value. And this one is the hazard factor. That's the Z factor that we talk about. That's the 0.4 if you're in the zone 4. And this one is the importance factor. So if you want to design your building with a higher PGA, like what the code says, just multiply it with 1.5. 1.5, I think, correlates to a 1,000-year earthquake. Other codes are 1.8. So 1.8 correlates to a 2,500-year earthquake. So that's that ratio there. So ratio applied to PGA. So that's increasing the base shear. And just doing that calculation there, just assuming that's the C1 and then just doing the algebra of this one, you will be able to get this value over here. And because your C1 over Z, so when you will just get C1, Z will move here and Z will over here. So Z will cancel. So that's the value you will have here, 2.5 CAI. And another one, C2, which is another Z at the denominator of CV. So that's what you get. That's what you get there. So that's the background of code-based shear expression. Hopefully you've understood a little bit of that. So when R factor equals 1, so meaning when your R factor, your response modification factor is 1, so your structure is responding elastically in the from the earthquake, which is equivalent to that F elastic. And then moving forward, and then with these two equations, it forms this one. It forms that. So R value is a very simple factor, your response modification factor, yet a very important characteristic of the building. It's also important to really understand the purpose of this value. Maybe later on, I can insert the deeper explanation of what this R factor is and why we are, because sometimes to others it's sometimes counterintuitive because we are designing buildings for earthquake, but why we are reducing earthquake force. So that's the reason behind why R is in the denominator, and we will hopefully I will discuss that further. So yeah, that's the 5-year engineering degree in a few minutes. Hopefully that was a few minutes. And yeah, that's the last bit of my slide. Thank you. Hopefully you understand something from this one.
Thank you, Engineer Valencia. So again, thank you, Engineer Valencia, for that informative presentation. Now we will move forward to our Q&A portion. So we will read some of the comments or some of the inquiries of our attendees. So may we call again Engineer Mamoko and Engineer Valencia to join us again. So we will start with Engineer Arthur. So again, sir, this is the first question from Mr. Edron Abrera. So his question is, sir, paano sir minomodel yung cables doon sa shoring tower?
That is a very good question, actually, because normally we don't model tension-only members. We just model stick like beams, columns. But that for the shoring tower, you can model that one using the cable and tension-only member specification. But see to it that the cable, you have to specify the initial tension, which is, for me, I put that around only 2 kilonewton just to make the cable stretch a little bit, or around 200 kilograms. So by that, I will show you on the screen. Okay. If you can see my screen, I don't know. So that modeling is only tension only member, and the section is prismatic. You just put the diameter, and then that it's good to go. So you will have force on that cable, and at the same time it will resist on different movements, but only tension, not compression. So that's the answer.
Okay, sir. So there's another question from Mr. Edward Atienza. Sir, ano pong code ang ginagamit para sa allowable joint and member sa design ng scaffolding? And a follow-up question is, anong code ang ginagamit para sa drift check?
Okay. For the drift check, buildings or towers or anything, normally we use the UBC code, Uniform Building Code. But for that scaffolding, because scaffolding is temporary materials in nature, so we have in the 2009 manual in Australia, they put that scaffolding manual, and also if we use American code, you can use the ASCII 37-2 2002, and you can find there the good guidelines for designing scaffolding materials, especially the joint connection, like using swivel clamps or whatever pins you have. That's the answer.
Thank you, Engineer Mamoko. So we will go to Engineer Valencia. So Engineer Valencia, there are some questions on our chat box. So number one, from Edward Atienza again. Engineer Valencia, if there are joint shear and joint flexure failure for columns and beam, what should be done on the design?
For this kind of failure, these are brittle failures. They are not ductile failures. So in the design, I would recommend not to these mechanisms to go away with this kind of mechanisms. No, that's why there's what we call capacity-based design. So that's part of my lecture for the next session, capacity-based design. Because you do capacity-based design, you design first your electrical fuses. I will just liken it to as electrical fuse. You design your electrical fuse, or you design your plastic hinges, and then you design your joints, you design your column, and you design the remaining segments of your beam, referencing to the strength that is being squeezed out from your plastic hinges. For example, if your plastic hinge is in a given joint, let's say you have a beam on the face of that column, you have a plastic hinge that's maybe have a plastic capacity of, for the sake of discussion, let's say 100 kilonewton meter. In the analysis on your columns, from your structural analysis, let's say the moment on your columns is just let's say 70. Do not design that column. Do not design that column with a 70 kilonewton meter. Design your column with the plastic hinge capacity with the overstrength factors of your beam. So if you have a plastic capacity of your beam which is 100 plus your overstrength factors, let's say 1.2, so 120. So you design your column with 120 kilonewton meter, not the 70. And the same for the joint. You design with a joint from that force. So I won't recommend any shear failure is a brittle failure, and brittle failure, your structure will not realize the assumptions you made in the beginning. For example, in the beginning, you used an R factor for a special moment resisting frame. You use an R factor of 8 or 8.5. So that's in the presumption that you will follow all the requirements of the detailing of seismic moment resisting frame. But if you miss those things, so your assumptions is no longer in align with what the outcome of the design is. So yeah, so move away with those brittle failures. Hopefully I answered that question.
Okay, Engineer Valencia, thank you. So we have another question. So from Andrew Rebuyas. So sir, may tanong lang po ako regarding composite beam column joint design analysis subject to lateral earthquake motion. Ano po kaya yung magandang i-improve sa design ng composite beam column na strong to earthquake, especially the big one that we are preparing in Metro Manila?
Like I mentioned, if we are talking about like joint design of the joint sa design ng composite beam column na strong to earthquake, especially the big one. So my understanding your question is composite beam column is you are using a composite material. So maybe you are using a steel and concrete, or maybe concrete and some other materials. But really in globality of the design, whether what kind of material you are using, always do to improve performance of your building, always do capacity design. And if you want to increase the resiliency of your structure, don't just rely on your column joints or your beam column joints as the source of ductility of your structure, or your plastic hinges as the source of ductility of the structure. Remember, if you have used an R factor of 8 or 8.5, so for me, we can design a building to dissipate the same amount of energy, but with less damage to the beams, to the columns, and to the joints. So I hope I answered that one as well sa question yang ano pa kaya ang magandang i-improve sa design ng composite beam column.
Okay, Engineer Valencia, so I have a personal question at hand. So this is my question. So right now in the Philippines, we are now using, or some of the structures are using seismic pad isolators, especially
Yes.
in the Philippine arena. I know that it has been used. So
Yes.
I would just like to know if we can adapt it to high-rise buildings, because I'm thinking that the seismic pad can be compressed too much if it is so much weight that it will carry. So that is my question. Can it be applicable to high-rise buildings here in the Philippines as well?
Yes, actually it can, but you know, the isolation, there's what we call the isolation interface. The isolation interface, which is which means where your isolators are located. It could be located on the base or any level of the structure you want. It could be there's a in one of conferences before that I have, although I'm not involved in that kind of project. In one of the conferences I've attended before in China, they were doing some research that it's a high-rise building, but they're trying to put the isolation plane at somehow in the 2/3 height of the building. So it reduces the building. I mean, it reduces some response on the building. But for high rises, for me, if you ask me personally, for high rises, high-rise buildings already have long periods. So if for a shorter building, you will put a base isolation there. What you are doing is elongating also the period of the building. So if your period of the building, going back to that response spectrum I have shown, if your period is already in the 2 seconds, 3 seconds, or 3.5 seconds, you've already significantly reduced your seismic forces in your building. So if your high-rise building is also already in the 3 or 4 period, 3 period range already. So I mean, for me, it's not so beneficial for the building. But there are other systems you can use to make the building increase resilience, such as like if you're using seismic dampers. Other than seismic dampers, you can viscoelastic dampers. There are other systems that we can use. But going back to your question, if these isolators can be used, yes, they can. It depends on what level you want and the capacity of your the capacity also of your isolators. So they have also, yeah, you're right. They have limited axial capacity, and they have also significantly reduced tension capacity. And high-rise buildings have very much high tension tension forces in the on the base. So that's things that needs to be considered as well when if you're using seismic isolators for tall buildings.
Okay, sir.
Hopefully,
But
I understand it.
yes, sir. Last question, sir. Is it costly to use isolators?
It depends on the size, probably no, on the size of the building. I will not probably sugarcoat this kind of systems if you use this. There will be some premiums, no? There will be premiums that you will be paying in uh, in building the structures with base isolators. But I will probably not say that they will be cheaper than the traditional ones. No, they will not be. But there will be a cost involved in that because but there are also some limitations on the building because, for example, if you have a building, it's also relative to like the square meters of your building. If you have a, let's say, a square lot, which is yeah, for the sake of discussion, you have like a 1,000 square meter square lot. If you use base isolators, you cannot hindi mo pwedeng isagad yung building mo doon sa property line. You cannot do that with doing base isolators because you need to allow your building to move around within that boundary, property boundary. You need to allow that to move. And if you will construct a building na sinagad base isolated siya and then sinagad mo sa property line, and once it moves, babangga yun siya doon sa katabi mong building. If yung katabi mong building is nag-construct din na sinagad din niya doon sa building mo, yung building niya, so magbabanggaan yung building. So normally for base isolation structures, you need to offset based on the requirement of the design. You need to offset the perimeter walls of your building to allow this movement. So probably in terms of square meter, yes, tataas siya because liliit yung square meter area ng iyong building.
Okay, sir. Thank you so much for that answer. Due to the interest of time, we will now be limited to just last question. This is from John Ford Pagirigan. So, Engineer Valencia, what retrofitting methods are available now so we can reinforce the existing ductile buildings, which is designed as per NSCP, and convert them into an EQ, resilient, and low damage design system as you discussed?
Yes, we are working with, at the moment, we are working with couple of projects. It's an existing building. No, sorry, only one because the other one was a new one. But the other project that we are working at the moment is I will just not say any details, but it's in Davao City. So it's an existing concrete building, yeah, reinforced concrete building. It's a ductile building. The systems we use is using viscous dampers. So but what we are planning to do here is, because when you use viscous dampers does not add stiffness to your building. What we are trying to go away is to add more forces in the building. So we don't want to do that. If you add braces like the conventional steel braces, it will reduce displacement, but it will induce more forces. It will attract more forces because your building is getting stiffer by adding those braces. And your building is, once your building is already constructed, you have already the foundations, and it's difficult to retrofit foundations, especially when already there's other buildings also constructed, and the disruption in the operating of that business. So what we have decided to use is to use viscous dampers on selected areas for this one. And the other building, which is a new building, but I think that can still also be used for existing building is uh, a, a system which is, I will also present it on the next session, which is what we call the RSFJ. It's a resilient slip friction joint connection. So it's it's a steel building, so it's more fit for a steel building, in my opinion, because what it contributes to the building is after there will be no plastic hinges. All the plastic hinges will be in the connections, but there will be no damage. We will be able to provide the required ductility, but no damage. And at the same time, after the strong earthquake disappears, the building will be moved back to its original or its undeformed position, or I mean its original position. So I can say probably viscous dampers for an existing one, or an RSFJ for an existing one as well.
Thank you, Engineer Valencia, for answering all of our questions. Again, thank you, Engineer Maboko and Engineer Valencia, for answering the Q&A portion and for our fourth webinar session for today. To show the appreciation to your presentation for all of us today, we will be going to award the certificates for our two guest speakers. And this will be the content of the certificate. So the certificate of appreciation is this is awarded to Engineer Arthur